Good morning, everyone. Thank you again for coming to the third annual Water Board Data Symposium, Day 2. Welcome back for those of you that attended Day 1. We had a great group of presenters really focusing on the disruptive changes themselves and kind of the path forward, and maybe some solutions on management-oriented ways to collect data and data that we should be looking at. Today's going to be a lot more focused on data itself and what we can do with that data, both current and in the future. It's really kind of exciting what we're, Day 2 is what I've been looking forward to. We got a lot of cool presenters and showing how we can visualize data and turn it into information for managers and for the public, and to make it available for people to innovate. So we got a great group of speakers today too that I'm excited about. For those of you that weren't here yesterday, I'm going to go over some of the logistics. Sorry if it's repetitive for those that were here. First off, restrooms are straight out the auditorium doors and to the left, and another left there, right there. The general format of the day is going to be presenters that do about 15 minutes on a topic with about a 5-minute Q&A. And then there are a few panel discussions, a great management panel discussion later on where we got speakers like Jonathan Bishop and Steve Weisberg, as well as Jimmy Smith from the San Diego Water Board, to talk about how they, as upper-level managers and decision makers, want to see water and the data presented to them to make their job easier moving forward, as well as the unveiling of the 2018 Water Quality Status Report, which is really kind of a data story of how we take data and make it into information and show it visually to make it informative. So really cool there. And there's going to be an opportunity to talk with the contributors to that data story. First off, we got Jay Davis from the San Francisco Estuary Institute.
I'm sincerely thankful for you folks being here. If anybody's looking for a seat, there's some room in the front. But I'm happy to be here today to share thoughts about the future of bioaccumulation in California. I think it's a kind of applied science fiction that's fascinating and fun to think about. This figure is showing a map of location of fish consumption advisories in California from the state website. And the first message is that California has a bioaccumulation problem. Bioaccumulation is the accumulation of contaminants in fish and shellfish, wildlife, and humans. And a great indicator of the extent and magnitude of the problem are these fish advisories. There are many advisories across California and many of our water bodies. We have statewide advisories for the coast and for reservoirs that don't have specific advice. So in the face of all the change that we're facing in California, it's interesting to think about what the future holds for bioaccumulation. As we heard yesterday, and as was well stated by Bob Dylan over 50 years ago, still true today, the times they are changing. And Bob actually was very prescient. He had songs on this album about climate change, land use change, water use change. Other important categories of change that weren't talked about much yesterday, but definitely affect bioaccumulation and other water quality issues associated with contaminants are chemical use and pollutant emissions. So I want to look into the crystal ball about what the future holds for bioaccumulation over the next 50 years. This slide showing a list of some of the pollutants that are of greatest concern and most notable for California. I'm only going to talk about a couple of them, mercury, algal toxins, and I'll say a little bit about dioxins and emerging contaminants. I'm going to focus on mercury. Mercury accounts for, I would say, about 90% of the bioaccumulation problem in California, and it's a statewide problem, and it's a relatively severe problem. It also is a contaminant that will be affected by disruptive landscape change in interesting ways. So it's an interesting contaminant to focus on. So the mercury problem in California was actually born from disruptive landscape change 150 years ago with the gold rush and the birth of California as well. This map shows the locations of gold, silver, and mercury mines. The gold's in yellow, silver's in black, and mercury's in red. I'm glad the projector's working today. The miners very quickly covered the state and looked under every rock for these precious metals. The mercury was mined primarily to be used in purifying gold and silver, so it was taken from these mines in the Coast Range up to the Sierra Nevada and across the state, and was released in the process of purifying the gold and silver. So not only did the mines disrupt the landscape, but there was a tremendous change in the plumbing of our mountain ranges to get water to use in the purifying process. And then also hydraulic mining took vast quantities of water and blasted away the hillsides and created a massive disruption of the sediment geomorphology of our waterways. In the process, spreading mercury throughout the streams and rivers and down as far as San Francisco Bay. So 150 years later, we're left with a persistent problem that is largely attributable to mining, but there are also other sources, or global sources of mercury that's transported through the atmosphere. And so it's both a local and a global problem. This map is showing data on contamination in sport fish based on swamp monitoring from 2007 to 2011. We did a series of statewide surveys of lakes, rivers and streams and the coast. The red dots show concentration high, and orange and yellow are also contaminated with more moderate levels, but it's clearly a statewide problem. And we see high concentrations, notably both in areas where there's mining influence, but also in the few areas that I could try to pick out where they're removed from mining influence. So one of the key message I want to convey from this figure is that there's enough mercury throughout California to potentially create a bioaccumulation problem. The key factor is mercury cycling. It takes a small amount of mercury to supply enough to create a bioaccumulation problem in a water body. Mercury cycling is really critical and can determine whether you have a high concentration or a low concentration. So I want to take a quick look at the mercury cycle, which consists of the process of basically two key categories of processes, starting with the formation of methylmercury, and this is the toxic form that accumulates in the food web, and this is a process that's primarily driven by bacterial activity. And then once the methylmercury is produced, it moves up through the food chain, increasing concentration at each step along the way, and then reaching very high concentrations in sport fish, with concern for human exposure, and then also in wildlife. So thinking about the future and what all this disruptive landscape change and climate change means for mercury, we need to think about the effect on methylmercury production. So this first category of processes. So these processes are primarily bacterial activity. There's a couple components. Methylation is a process the methylmercury is produced as a byproduct of bacterial metabolism. It's primarily by bacteria that like to live in low oxygen conditions, such as you come at the bottom of a reservoir or in a wetland. Demethylation is another important process with another set of drivers. There's biotic and abiotic pathways for demethylation. One of the most important ones is photodemethylation. The sunlight can cause the loss of the methyl group from mercury. And then given the importance of oxygen and sunlight, algae growth is very important. And there's a number of factors that can influence algae growth. So you can see this is getting complex already. Then there's the food chain transfer part after the methylmercury is formed. And the processes that are important here are primary productivity, basically the structure of the food chain and the energetics of the species, the growth rates of the species, who's eating whom, and which habitats these species are using can all affect the amount of methylmercury accumulation at the top of the food chain. So I have a list here of the landscape drivers that could potentially affect mercury cycling, and just going through them quickly, there's a lot of complicated biogeochemistry behind all of these, but of course emissions can influence methylmercury formation. Climate change factors like flooding, which creates anaerobic habitat with a lot of organic material. Drought can affect water levels in reservoirs and algal populations, growth rates. Fire can alter the movement of water and sediment and chemicals off of the landscape. Temperature can obviously affect the metabolism of bacteria and other species. Land use change, kind of like fire, can affect water runoff and the chemistry of the runoff, including nutrient loads, which control the algal populations and production in the food web. Habitat restoration. Wetlands are, we've lost a lot of wetlands. We need more wetlands, but wetlands have low oxygen environments, and they're associated with relatively high methylmercury production. Green infrastructure can influence production by altering the transport of contaminants to downstream water bodies, but then also is creating habitats that could potentially be conducive to methylation. Then there's a number of things that apply to reservoirs, but also other water bodies, like water level fluctuations, the oxygen status of a water body, stratification. So it's quite a list of things that could potentially affect methylmercury production and food chain transfer. Which of these drivers do you think could affect methylmercury production? All of them. And then for food chain transfer, pretty much all of them can affect food chain transfer as well. So it's quite a complex picture, and many drivers can be influencing mercury cycling. So what's the mercury forecast? It's very, very hard to say because it's very complicated. In other parts of the country, there have been regional trends observed, downwards and upwards, downwards and then upwards. But we don't have a good data set, a good statewide or regional data set in California to know what's happening across California. I think there are probably going to be reduced impacts of mercury, reduced concentrations in the next 50 years. I think TMDLs will have an effect. I think reduced global emissions due to the switch from coal burning to more renewable energy sources is going to be an important driver. So I think concentrations will probably be lower, but I have to say probably because climate change and all these landscape drivers could slow the progress. So it's really important to monitor, to ask the fish, and let them tell us what's actually happening. So quickly on algal toxins, another major concern, bioaccumulation concern across California. We have problematic concentrations. Coastal bivalves, there's an annual quarantine of mussel consumption due to algal toxins. There are often die-offs of birds and marine mammals on the coast, also invertebrates. A notable case shown here, sea otters near Monterey, where there was mortality runoff of in freshwater invertebrates like bivalves. This has been levels of concern have been observed in the Klamath Basin. And then recently in San Francisco Bay, we've seen microcystin, a freshwater toxin, accumulate in bay mussels. And we also have paralytic shellfish poisoning toxin recently observed to accumulate to levels of concern in the bay. So there's a lot of problematic concentrations. Concern is rising, and climate and landscape change will be important. Randy Turner will talk more about this in the next talk. And I want to talk quickly about fire contaminants, and we talked a lot about fire yesterday, but I think we need to be giving more attention to bioaccumulative contaminants that could be associated with fire. Mercury is stored in vegetation on the landscape, and when there's a fire, it can be released to the atmosphere or move to the soil and then run off from the soil. Along with the changes in water flow and sediment movement, you can have greater mercury flux, and there have been studies that show increased mercury in lakes downstream of burned areas. Dioxins are formed from combustion of organic material like forest fires or other types of wood burning. And I think water bodies downstream of burned areas, reservoirs downstream of burned areas, if there's significant fishing in water bodies downstream of burned areas, there's a potential for higher concentrations of dioxins. And dioxins, even though they are at sort of background levels, the concentrations still are of human health concern widely across California. And then emerging contaminants are another possible product of fires when more urbanized areas are burned with structures, households, businesses. There's a lot of chemicals that we have in our buildings that burn and form. They're considered emerging contaminants before they're burned, but then after they're burned, they become different forms of emerging contaminants. And this is something that we don't have a lot of good information on. The Regional Monitoring Program for San Francisco Bay is doing a study of this, but we don't quite have the results of yet based on the North Bay fire. Another category I want to mention is water use, and we're on the brink of really drastically changing the water cycle, especially in urban areas, through the implementation of green infrastructure to capture rainfall and runoff. We're also looking at trying to create habitat from wastewater. One of the major trends is going to be recycling of water, which recycling of wastewater to potable water. That leaves all the contaminants get concentrated into it's called a brine or a concentrate that we'll still have to figure out what to do with. And one of the ideas is to dispose of the brine or put the brine in wetlands because we're not sure, we don't really have great ideas or other ideas for what to do with it. So it's kind of using features like that as filters, which I think there are benefits of, and clear benefits of doing that, and there is some true filtration that can happen for things like nitrogen. Nitrogen can be removed from the water stream, but the persistent bioaccumulative contaminants that are in these streams some of them won't get degraded, and they'll accumulate in these filters, and filters get dirty. So this is an air filter, which is what my house air filter looks like by the time I get around to changing it. filters get dirty, and there are contaminants that we need to think about in wastewater and stormwater that can be accumulating in these filters. So as we revamp our hydrology, we need to think about contaminants. I don't think it's a showstopper, but we need to think about the contaminants, where they'll accumulate, monitor, and if they're accumulating to problematic concentrations, try to get them out of the water stream or figure out other management approaches. So what are some monitoring needs for the next 50 years? First, I think there's a need for statewide monitoring, and particularly for the two biggest statewide problems, mercury and algal toxins. And we need to update the public on the status of the contamination, and then we also need to track trends. And this map is showing one of the priorities for statewide monitoring. It's a map of 200 bass lakes that we have set up a cycle of sampling these. We sample them in 5 groups, and every other year we go out and sample one of the groups. And since we've randomly selected the lakes from this pool, each time we go out, we get an estimate of the average, the statewide average for bass lakes. So we started this in 2015. Over time, we'll have a good time series to know whether on a statewide or regional basis, mercury concentrations are increasing or decreasing in response to management and then other drivers like climate change. Algal toxins, there's statewide monitoring on the coast that I think is important and should continue. So those, I think, are the key statewide elements. And then we need targeted monitoring of other selected water bodies. And a couple of categories of those, certain water bodies like San Francisco Bay have significant problems, but also there's a lot of interest in that water body, and there's a great monitoring program there. And then other targeted monitoring should occur in sort of worst case scenarios to see how bad the problem is, and then potentially, if problems are detected, that could lead to statewide monitoring of those things. So I think that kind of monitoring is needed, both for updating status, tracking trends, and then also addressing information gaps on topics like algal toxins, fire contaminants, and CECs. And then overall, I think we've got a pretty good framework in place. It's a pretty cost-effective framework with SWAMP, the Surface Water Ambient Monitoring Program, covering the statewide elements, like that Bass Lake monitoring, and programs like the Regional Monitoring Program, the BITE program in Southern California, and others, supporting that with more intensive studies. So we need to sustain that, and that's a pretty good structure. But I think we need to do some expansion to address information gaps that exist. But I think a coordinated effort led by the SWAMP can meet all of these needs. And if we stay the course on monitoring and management, and we implement some of the visions that were presented yesterday, and that more good ideas are on the way, I think California has a brighter future ahead for water quality. Thank you.
Thanks, Jay. If you guys have any questions, raise your hand, and we have 2 mic runners.
You mentioned a loss of wetland habitat in California, and I've heard different figures from we had 2.3 million, 4 million. So what is the total acreage of wetlands in California?
I don't have that number in my head. I know we've lost. Well, I have some of the numbers for San Francisco Bay in my head. We've lost over 90% of the wetlands that were there. There's pretty ambitious restoration efforts underway in the South Bay and the North Bay to replace and restore those wetlands, like thousands and thousands, maybe in the range of 30,000 acres that are being restored. So those are the numbers I can give you. The question was, what is my wish list for fabulous new monitoring techniques? I think one of the key ones is better and cheaper chemical analysis. mercury is not that expensive to analyze, but the other contaminants, like emerging contaminants, are very expensive, and that really limits the amount of work that's been done. I think technology is going to advance, and that will become less of an obstacle. It's still, when we do our fish studies, about 80% of the cost is collecting the fish. So that's still the biggest cost, but I think if we could reduce the cost analysis, that would be pretty huge. The other question is with regard to wetland restoration. What's been the conversation with mercury concerns versus the value of restoration? And the general sort of conclusion of that kind of conversation is that in the mercury researchers all agree with this, that mercury is a concern with restored wetlands. It shouldn't be a showstopper. The restoration is needed. We need those habitats, but we should monitor to make sure that we're not creating a severe problem. And there's been some work on this in San Francisco Bay, and that's where I'm most familiar. And the monitoring so far has shown that there isn't a big increase in mercury as we restore tidal marsh, salt ponds or managed ponds to tidal marsh. So that was a big concern. That with monitoring data, I think the level of concern is diminishing. But there's mercury science has not really advanced to the point where we can confidently predict what's going to happen with any particular project. So I think it's still key to ask the fish, ask the wildlife in these situations to see if they're seeing a spike in mercury, or I think a short-term spike would be of less concern than sort of a shift to higher concentrations that lasts over time. So far we have good news, but I think we need the restoration, so that's got to go forward regardless. Thanks.
Great. Thanks, Jay. As the director of the California Water Quality Monitoring Council, I'd be remiss if I didn't mention that Jay is also the chair of the Bioaccumulation Oversight Group, which also is responsible for creation of the Safe to Eat portal. If you guys are interested in staying informed with that, you can contact me or Jay, and we can get you in touch with the right people. And also the gentleman that inquired about estuaries, we have a wetland monitoring group as well as part of the monitoring council, and I can put you in touch with them to keep you informed on the new information as it comes up. Next, also from the San Francisco Estuary Institute, is Randy Turner, and he's going to be talking to us about how we can use satellite imagery.
Thanks, Nick. Welcome, everybody. Really appreciate you being here. So there are a lot of ways that we've been collecting data on cyanobacteria, but often that's done in very point-specific locations and very infrequently. So we're talking about using satellite imagery to really paint a much bigger picture of what our cyanobacteria concentrations are. So, there we go. I'll just use that. That's fine. So, one thing, I guess the first thing to say is, cyanobacteria and the toxins they produce are natural. They've been around for a long, long time. But one thing that's not really natural are some of the changes that humans have done to the environment that have affected the factors and the drivers of cyanobacteria blooms. So as we change landscapes, we've seen over the course of the last day, that some of that historical ecology and how we've impacted watersheds. We look at climate change. All these things are driving some of these these factors that influence cyanobacteria blooms in a way that's that's generally not very good for public health. So as water temperature increases, as eutrophication increases, and as flows are reduced and we increase the residence time of water through reservoirs, all those factors generally lead in favor of cyanobacteria blooms. But unfortunately, it's not just a matter of controlling phosphorus or, any one particular factor. These blooms are, the factors that drive cyanobacteria blooms are very complex. They vary by watershed, so there's no silver bullet to addressing cyanobacteria that we've seen so far. And that really makes, managing and trying to control blooms a real challenge. It's a very complex picture. And when we talk about, the amount of monitoring that has occurred, we just don't really know much about it. And that's where I think the advantage of satellites come in to really provide a great complementary data set to what we've collected on the ground. So, the goals of the project that we're doing here is really to provide this estimate of cyanobacteria abundance in kind of a near real-time manner for larger water bodies across the state. What that's going to allow us to do is really create a screening tool to help guide public health officials to go out and sample when it's appropriate. So we'll be able to tell them where and when cyanobacteria blooms are forming so they can go spend their monitoring dollars more effectively. But it gets beyond that because the satellite data is collected, every other day as the satellite flies over, as long as the weather's good. So we're really able to see some really great spatial and temporal trends of cyanobacteria abundance and really be able to, use that data for quite a few other, projects and other natural resource management questions that we may have. So this really, while the intention was focused on public health monitoring, the data set is really valuable, and we can get beyond that if we, expand this data set out and start combining it with other information. So we've been working under contract with the California State Water Board and SWAMP to really do this project. So we have to shout out and give our thanks to the State Water Board for this work. We've been working in coordination with NOAA, who does a lot of the image processing. And so we've really been developing the infrastructure to process and display this data. And really we're focused right now on two separate satellites. Both are managed and put up in the air by the European Space Agency, so this is very much a collaboration. But there was an older satellite that's since taken a long nap. So we have about 10 years of data from that satellite from the early 2000s. And there is another satellite that went up in 2016. We have data available from January 1st of 2017 forward. And so that gives us data every other day. But there's a second satellite that it's twin that's now been launched, and we should expect to see data, probably by the fall or if not the winter. So then we'll have a repeat cycle of roughly every day. So that'll really, again, give us great information on a near real-time basis. One of the great tools that we put into this is not only to display the data, but create notifications that can go out to regional board staff and other people to let them know when these blooms are developing. So it'll really act as a good early warning system. So some of the basics about satellite imagery, without getting too much into the details about spectral analysis and everything, is there's these satellites are pretty unique in the sensors they have. I will say that, and because of that, we're able to really say when there are cyanobacteria blooms, and we can distinguish them from other algae. So there's really two data sets that we get from this. We get the cyanobacteria abundance, and we also get the abundance of non-cyanobacteria. So we can distinguish that. And so for a satellite that flew overhead yesterday around noon, that data is processed overnight, and we have it up online on the website by the morning. So it's not quite real time, but it's pretty close. So every time the satellite flies overhead, it's looking at individual pixels of information and estimating an average concentration of cyanobacteria within a 300 by 300 meter pixel. So basically the average concentration over about 22 acres. So it's very much a rough estimate, but we feel pretty good in most of the data we see. One of the really nice things is every time it flies overhead, it's looking at pixels in the same exact spot. So we can really then take that information and talk about what's happening over time. So while there's a lot of really great aspects of the satellites, they're not perfect. If there's clouds or fog overhead, sorry, nothing. Even if, situations where there might be high wind on the water body and creating white caps, that might create glare that again impacts the reflectance off the water and the ability for the satellite to tell us the story. it's pretty sensitive, sensors, but it's really only going to tell us the total amount of cyanobacteria, not what species are there that are producing or can potentially produce toxins. So, and it definitely does not measure the toxins themselves. So in terms of the connection to public health and some of the thresholds we have established to put out water body advisories and postings, there is definitely a disconnect there, but it's still going to be a great screening tool to help guide that sampling that will need to happen on the ground. We have noticed some false positives that we think are based on certain environmental conditions that were unexpected in California. When this has been used elsewhere in the country, they never had to deal with high altitude lakes. And we also have seen some potential issues in hypersaline water bodies, interference with halobacteria. So we're working with NOAA on some of those issues, trying to identify the where and when we're seeing these issues, and we think it's not likely real, and they're working on how to fix it. So and correcting the algorithms that process it to try to clear that out. At this time, again, that satellite is looking at fairly large pixels, so we can only really work with large water bodies in the state. But there's work being done on a couple other satellites that have a much better spatial resolution. When we talk about quantifying, these estimated abundance values, we're working with a very unfamiliar metric called cyanoindex, or CI. So, basically it's not really relevant outside of the world of satellite imagery, so it's hard to compare to some other things, but we really want to focus on that. We want to try to simplify it. We've converted CI numbers into whole numbers that range from 1 to 309. And within that, we're also trying to take values and provide information in a more simplified format based on some World Health Organization thresholds for cyanobacteria that put things into bins of low, moderate, and high concentrations. So again, because those CI numbers are a little bit obtuse, it's nice to be able to simplify things when needed. So all this has ended up producing a website, a data visualization tool called the SinoHab Satellite Imagery Analysis Tool. So it is live online. You can go to it. Try not to do it until I'm done speaking. Right now, it's definitely still under development a bit, and we're waiting for final approval from the state board on getting it up on their app portal. We think it's going to be a great complement to the information that's already on there. Right now, because of some of those false positive issues and waiting on some field verifications, the data is provisional. So if you're using it, please use it with a little bit of caution in mind. The last slide showed just the big entry page when you get in, but really the meat and the value of the tool is once you zoom into a water body and select a water body, what you're going to find is kind of three different portions of the website page. So you have spatial information on the left, and on the right-hand side you have two different charts that provide some water body-wide statistics. And as much as our eyes gravitate towards that spatial data, really I like to start with the chart in the upper right, which is kind of a longer time series, and it provides us kind of that understanding of what we're really seeing. And one of the reasons why, and that basically provides, we can see the shaded area there is kind of the mean data. I guess the mouse cursor, yeah, so we see the mean data here. And for those in the back of the room, there's actually a line above it that's the 90th percentile data, which has a little bit more relevance to public health management. And the reason I like to start with that long time series is because there's a small window here on the far right that you can move back and forth, and as soon as you move that window, that changes the information in both that spatial data section as well as a detailed time series to see what's happening in that small little window. So if I went online, you could move that around, and it's really a great thing to play with and try to explore your own water body and see what's happening. So one of the other interesting developments we've done is be able to pull in data from California's environmental database, CEDN, and allow it to display data alongside the satellite imagery. So when you select a water body, you can look for, in the long time series, there's vertical lines, and that shows when there is CEDN data available. So you'd go in and you'd select your parameter, whether that's a general water quality value or it's a toxin value, and be able to compare that to what's going on in the water body. So you can see it's so hard to see, but there is a kind of a faint outline of the general trend in the mean values from the satellite imagery up here, and then there are discrete data points from, in this case, chlorophyll A. And so when you hover over one of these diamonds, it'll increase the size of the diamond on the map, and so you can see where that site is. And then you can see the relative value of, in this case, chlorophyll. So it's a way to really link some of this valuable discrete data that's out there with the actual satellite imagery. The problem is there's not a whole lot of that data in SEDEN. So if I will put a little plug in, if you have any sort of data related to water quality or HABs in your water body, please upload it to SEDEN so we can again expand the value of this tool. Besides all that, you're able to download data in a variety of ways. You can download water body-wide statistics, both from the satellite and then as well as some that SEDEN data I just mentioned directly from the tool. So you can get, just export tables and put it in Excel. You can also download some of the spatial data. So you can pull in rasters and other mosaics from another location if you want to show what's happening and what the current conditions are. So in general, we have, over 11 years of a pretty massive data set for 255 water bodies. I will say we really stretched the number of water bodies we were trying to look at, and then about 150 with good, reliable data. There's, about 100 that are just borderline too small. So we get data occasionally for them, especially, when the water body's in full pool. But there's some that just, whether it's due to regular cloud cover on the coast or it's just almost too small to look at, we get occasional data, but there's still value in retaining those. So kind of summarize the data that's available. Again, we have lots of water body-wide statistics that are out there that are available on the tool and the rasters. But we also want to encourage people, if you have your own data sets and you want to take a deeper dive into this, we can provide the GIS data for the full suite here. So, we definitely welcome that because there's some data sets that you may not want to share or may not fit on SEDEN that you really want to compare to. So please let us know if you want to use that data. Because again, there's a lot of other opportunities to use this besides just public health monitoring. So whether you're managing natural resources or a water body itself, or just doing research, there's potentially a use for this tool and the data behind it. So I mentioned the public health monitoring, but if we want to look at compliance with PMDLs and whether we're achieving an improvement in conditions, this might be a value. Linking nutrients to biological response and biostimulatory conditions. If your water body is up for FERC relicensing, we can talk a little bit about the conditions and what's happening. Because we have the spatial component, we can look at how the location of where drinking water intakes are and how we might be able to adjust treatment processes to deal with taste and odor. So again, that's kind of a good potential early warning opportunity. There's a lot of other different uses of that are just on the on that potential list. I don't want to just go on about all those, but and I'm sure there's some that I didn't include. But really, I want to start this conversation with you. And if you think of other opportunities to use this data, we want to hear from you. We want to figure out what's next. How can we make this helpful to you? So in terms of some of the bigger picture next steps, there's a national program called the Cyanobacteria Assessment Network, led by a kind of suite of federal agencies, and they're looking at doing what we're doing here in the state. So they've been really appreciative of our efforts so far to really create this data visualization tool. And so whether it's they're incorporating aspects of what we've developed or potentially adapting the tool that we're working on, we want to be able to see it used not just in California but elsewhere as well. There's just a lot of value in that. But before we get too far ahead of ourselves of bringing this nationwide, we do have some field verifications to do starting this summer. And that gets back to, addressing some of the, the general accuracy of the satellite data. How much can we rely on it? in terms of really quantifying the blooms, and as well as addressing some of those false positive values that are suspect. We want to make sure that we're reporting accurately here. And so, we'll be doing that by going out into the middle of water bodies, comparing and collecting field data, collecting a bottle like this and trying to compare it to that average estimate of, what's happening in that 22-acre pixel. So, there's some challenges there just at that spatial scale in comparing data, but it's definitely an important step and one we're looking forward to really help begin to tell the story. And so, a lot of limitations on that in terms of going out when the weather's right, when the bloom's occurring, and exactly at the time when the satellite is flying over. So it's not just a regular program that we can, plan too much in advance. In terms of some of the progress we're working on within the tool, we're really trying to take some of this complex information and simplify it in a way just to make sure it's more user-friendly. So that, is some of the text itself within the tool and these notification emails we've created. Working to improve and add to the data visualization aspect. So we've had quite a few different color palettes that we've been testing, but we know that the national program is going to be choosing a color palette soon, so we want to be consistent with that if possible. But also, some people are colorblind and won't be able to see colors well, so we want to be able to have the option to toggle over to a colorblind-friendly color palette. I mentioned the WHO thresholds that are out there, and again, that's another way to simplify the information and provide kind of a general, is it bad, is it really bad, or is it fine? And then, as we've worked with NOAA on some of these potential false positives, they've made corrections to the processing systems for some of the newer data, but they have yet to go back and correct the older data. So we're waiting to do that. There will be some, potentially some drastic changes in the data sets for some water bodies, and the other water bodies that probably won't change much, but we're looking forward to that correction coming soon. In terms of, kind of looking out beyond what we're doing now, we definitely want to continue to expand and build on the tool. There's other statistical analyses that we might be able to build within the tool, as well as create, easier ways to pull this data into R and look at it yourself. There's other visualization improvements we can make in terms of pulling in some of that data that's, the non-cyanobacteria data, just to tell a better picture about primary productivity. Gets beyond the public health goals of this project, but I think there's a lot of value there. And then in terms of being able to query data potentially beyond seed, is there data in federal databases that might be of value here? Is there other, can we pull in weather information into the data set, or potentially continuous data to compare to the discrete data that's in there? So a lot of opportunities to expand there. And, we could potentially build in data layers that are password protected. So, I mentioned earlier, drinking water intakes. We might not want to make that publicly available, but if folks from, Division of Drinking Water wanted to, have a layer with drinking water intakes, they could know when the bloom is about to come into an intake. So really a better way to protect public health. So that's what I have for now, and looking forward to giving you guys an update again soon when it's actually online and ready to go and up on the portal. But I'll take any questions. In terms of the total number of water bodies we're looking at, we are limited by some of the quality control steps that have come from NOAA and per their recommendations. So we're not just looking for a water body that has a single pixel of data available. We typically want to have at least 18 pixels available for any particular composite data set we're looking at in order to have some statistical significance to the data. So if there's 17 pixels available for that composite, we throw it out, unfortunately. There may still be data, use of that data elsewhere, but not for the statistics that we're producing. And so that right there, if you think about it, and any pixel that's along the edge of the water where there might be land and water, we have to throw that out as well. So we're really looking at water bodies. The ideal water body has a lot of open space, and it's not some, narrow arms to each, as it works up the canyon. So those are just more difficult to assess. In terms of all the water bodies throughout the state, well, obviously there's tens of thousands of them. And so, we can't go there, unfortunately. There is work, there's a couple other satellites that have different sensors, but much better spatial resolution that some researchers are working on that may help get to smaller water bodies. And so, but the jury's still out on that, still under development. But we're hopeful that that could be a very complementary data set to what we're showing here. But they don't fly over nearly as frequently, so there's some give and take there. Does that address the second part of your question in terms of kind of where we're going?
Yeah.
I wish I really knew. It may be that the other satellites that are working on with better spatial resolution, they might not really be able to successfully tell the story because they're using different sensors as well. So we just don't quite know. But, as we advance technology on drones and cameras, we may be able to outfit something with similar, or at least some function, to be able to do, flights over a particular water body. When the bloom's starting, let's go fly the drone up and let's go see what's happening. So there is a lot of potential, but we're not there yet. In terms of how the data is processed with the algorithms, NOAA does the majority of kind of the conversion of the imagery into the CI value, and that's for each and every pixel. We take and we put it into this kind of data visualization tool and be able to produce the statistics that drive some of the visualizations. So the majority is on there, and we don't want to take credit for that part. We'd rather that they've been working on this for a couple decades, so we'll follow what they're doing and not try to come in and reinvent the wheel. But yeah, it's done basically at the national level. It's a great question to talk about all the different approaches to satellite technology and remote sensing, and the value we saw in one of the vendor talks yesterday about the use of aerial imagery to assess fields and water use and pests and making sure plants can grow efficiently. So when we talk about all the different technologies that are out there for remote sensing, it does sound like an amazing thing to put it all together into kind of a more usable format. And that's right now that's not necessarily planned. I think we've mentioned a few times yesterday. Our silo is dealing with cyanobacteria, that kind of thing. I mean, one thing on the portal on California's My Water Quality portal, there is also a map for beach closures based on high bacteria levels. I don't think it's in the plan that are developed once we actually test for toxins. So that has relevance to where we want to go swim or not, as well as the bacteria closures. So that could be a data set where we're combining multiple values into a single map versus I want to go to the bacteria map, then I need to go to the cyanobacteria posting map, to say where I want to go swim or not. But there's because of the range of technologies and purposes, it might be hard to broadly pull them all in together, but there are probably some that we can combine in the future if it makes sense and it's feasible. .com definitely has some great resources, and we've been working with them specifically. So that's a great question. I did not plant that. The Planet uses a different satellite that has, like I said, much better spatial resolution. They have 4 specific bands in their sensor that look at the wavelengths of light. The satellites we're using have 9, so it really captures that cyanobacteria wavelength well. And what we're doing with the Planet.com is going occasionally and kind of ground truthing based on the true color imagery within the Planet.com's visuals to see, like, okay, can we see the bloom in their satellite data? It's not really something that we do to verify each and every bloom, but it's a helpful tool. And the fact that it has this good frequency of data as well as that better spatial resolution, it's a very good complement to what we're doing. Okay, thanks everybody.
Thanks, Randy. Thanks, Randy. Another shameless plug. There is a great poster out there about the harmful algal blooms portal. As part of the Water Quality Monitoring Council, so I encourage you to take a look and take a fact sheet and participate if you want to get updated when that great data set comes live and that tool set becomes available for everybody to use. Up next is Brent Phillips from the University of California, Davis. He'll be talking to us about our long-term stream pollution trends program.
So I work for the Grand Canyon Laboratory. We're the abalone logo there, and I wanted to thank the organizers of the meeting for putting our abalone logo so prominently in the program. I thought it was kind of cool. We don't normally see it out there in the world. So my silo is aquatic toxicology, and I work for the Grand Canyon Lab. It's the Marine Pollution Studies Lab, and it's one of 3 Marine Pollution Studies labs that are in the Central Coast area doing various forms of water quality monitoring, chemistry, aquatic toxicology, data management. And it's a name we've kind of shared for a number of years, and we're going to actually try to start working together more often in the near future. But what I'm going to talk about today is one of several statewide monitoring programs that are under the umbrella of SWAM. And the Pollution Trends Program, or SPOT, is looking at contaminants and toxicology and sediments throughout the state. And we already heard from Jay this morning talking about the bog, and we're going to hear about perennial streams probably from Pete Odie later on. And these are various statewide monitoring programs under SWAMP that are looking at impacts to receiving systems. So first and foremost, we are a trends program. SPOT has 3 main goals as part of its program, and the first 2 are to look at trends in sediment contaminants and toxicity and relate those trends to land use. And this third overarching goal is to establish a network of sites throughout the state. And so, we were talking about mercury monitoring with the bioaccumulation stuff. We have mercury numbers in sediment throughout the state since 2008, so we can look at things like that. We look at pesticides, other metals, some contaminants of emerging concerns, and legacy contaminants. We also look at the related toxicology, and for those people who don't really know what toxicity testing is, it's the exposure of animals in the laboratory and looking at a biological endpoint, whether it be survival, growth, development, things like that. And so we actually have a biological component that's laboratory derived that can match up with the chemistry that we're measuring in the sediments. We look at sediments because sediments are sources and sinks for contaminants. A lot of the contaminants we're interested in are pretty hydrophobic. They adhere to the sediments, and then the sediment is an incredible transport mechanism within these watersheds to bring the contaminants to our sampling sites, which are at the basis of the watersheds. So we go to a variety of places, both pristine and not so pristine. That concrete line channel there is by Iona Creek. It's in Southern California. It's about a mile from where I grew up, and this was sort of indicative of the type of creeks I played in when I was a kid. And so Dad always used to stay out of there. Say stay out of there when it's raining. That thing cranks when it's raining. People from SoCal probably know that. So one of the things that we do as a main part of SPOT, and it's a bit of a struggle actually, is we try to define the land use in the sites that we visit. And so typically we do this by delineating a watershed that's upstream of the site we've chosen. The sites are at the basis of the watersheds, or they're integrator sites. And so in delineating the watershed, we use GIS layers, we use the National Land Cover Database, and we try to get an idea of what kind of land use is happening within 3 different scales within the watershed. We can look at a kilometer away from our site, we can look at 5 kilometers, and we can look at the entire watershed. And so when you overlay this National Land Cover Database, the most recent one of which is from 2011, 2016 should be out by the end of the year, we can get some idea of what the land use is. And what we found with SPOT is that the land use at the 5-kilometer radius is the land use that's most indicative of what we're going to observe at the site. Seems to be the 5-kilometer land use has the most influence over what we're seeing at the site. Now this can be tricky because you can have a site or a watershed maybe that's dominated by agriculture, yet right near your site it's mostly an open area, or an area that's not ag dominated. state or for land use, it's you have to pin them somehow. And so what we do is we take urban land use at that 5-kilometer scale, and anything that greater than 25% of a combination of low, medium, and high impact development plus developed open space, we call that an urban site. Our agriculture sites are greater than 50% row crop and pasture, and then we have a third category, which is open lands or other. I know that the bioassessment group uses a fourth category of forest lands, but the definitions for the two categories are in alignment with their program. Of all of the watersheds that SPOT covers, and it's not a perfect map. There are some delineations that are slightly off, but I wanted to show it just to sort of depict the amount of coverage that SPOT has throughout the state, and our 3 color codes. I'm not sure if this is a colorblind palette or not, but that's gray, Jeff. I know Jeff's the one that's colorblind in the audience. So the gray sites down here are urban areas. We have orange to represent agriculture, green to represent other. And then there's this fourth category. There's 3 sites within the SPOT site list that meet the criteria for both urban and agriculture. So we have 3 of these combination sites. Interestingly enough, 2 of them abut each other right on the central coast. And you might notice from this map that that there's a lot of nested watersheds, so sub-watersheds within larger watersheds. That can kind of muddy our interpretation of the data a little bit, but when we're looking at that 5-kilometer scale, it really sort of clears things up. So the theme of this whole symposium is disruptive land use, or disruptive landscape change, and I'll make sure I get that right. And I always think of disruptive landscape change like the things we saw yesterday about fires and resulting, floods and things like that, sort of Mother Nature, act of God kind of things. Whereas the landscape change that we're mostly dealing with when we're going through our SPOT analyses is that slow creep of development in California. And if you guys have been reading these bullets while I've been rambling, you would see that 4% increase in developed land area between 2001 and 2011 based on the land cover database, and an increase in impervious surface of 8.8%. There's also been a decrease actually in developed open space, which are things like golf courses and parks, but a commensurate increase in medium and high impact development. So there is this slow creep of increasing development in California. There's also been an overall decrease in things like scrubs and grasslands, and as we heard yesterday, also agricultural lands. There's less agricultural land in California than there was. It change as you drill down into these sub-watersheds. So this is a watershed where up in Northern California is basically part of the Sacramento River complex, and we sample it at Butte Slough. And as we zoom in to these smaller watersheds within this larger watershed, you can see that the land use actually changes. The way we bin these watersheds actually changes. So we have these that are considered open actually nested within this larger watershed, which is considered agricultural. So it's an interesting way, interestingly difficult way to interpret the data when you drill down into it. But it's very interesting to look at it. Individual land use to see what kind of things we're finding at the Pitt River, Pitt River watershed versus what we're finding in this larger agricultural watershed. So keeping with this map theme, since my silo is toxicology, I want to talk about toxicity testing first and some toxicity testing results. I've just recently discovered Tableau, and so these are some primitive Tableau figures that will be presented in another way during the water quality status report in a much better way that Michelle has been so kind to put together for us, much better looking. But the toxicity testing that we do, we test these amphipods. They're Hyla astecta, they're resident amphipods in California. We test laboratory population of these amphipods in our sediments, and we look at survival. It's a 10 days, and we see how many of them live, and we see how well they've grown over that time. And so what I've done here is I've just plotted the last 5 years of our toxicity data as average mortality, percent mortality. And you might notice that the larger the bubble, the higher the mortality, and a lot of these large bubbles sort of relate to urban areas. We see a lot of toxicity in the urban areas. There's a little bit of toxicity in our, San Joaquin, River Valley watershed here, and a little bit in the open lands on the north coast, but by and large, most of our toxicity is associated with urban landscapes. Now, one of the things that SPOT has really been able to sort of elucidate over the years is the relationship between observed toxicity, the land use, and pesticides. We've been looking at pyrethroid pesticides, which are current use pesticides. It's a family of pesticides that you know, if you go to Home Depot and you go get ant killer, it's probably got a pyrethroid in it. And they're ubiquitous, they're really, really toxic, they're hard to analyze, they're expensive to analyze to, address Jay's wish list. I share that wish list of having inexpensive analytical work to tell us what kind of concentrations we have in our systems. But the pyrethroids are also associated with urban land use. They're used in agriculture, and in some regions, they're an agricultural issue more than an urban issue. But throughout the state, pyrethroids are mostly associated with urban land use. You guys might have noticed this ginormous dot right here. That's Bouquet Canyon Creek in Southern California. And that site has had an issue with pesticides since I've been monitoring it in the early 2000s. It used to be diazinon, but now they've moved on to pyrethroids. What's interesting about a site like that is this site is really quite an open watershed. If you go outside of the immediate area of the site, it's a beautiful Southern California hillside, rural kind of area. But there's just some really, really high pesticide use in I think just the mall or the urban area right adjacent to that stream. It's a very interesting site. But anyway, pyrethroids associated with urban toxicity, associated with urban, and the question on everybody's mind, I'm sure, is, are the pyrethroids causing the toxicity? And if you look at toxicity over time in the SPOT data set, it's about 1 in 5 samples year to year are toxic. And if you look at the alignment of the toxic samples and the pyrethroid concentrations, those concentrations do exceed the toxicity thresholds, and you can explain a large portion of the toxicity based on the pyrethroid concentrations alone. So that's probably that's the crux story of SPOT. So maps are great for giving this snapshot of what's going on, statewide, but I still like using graphs like this one and like the one on my data dive tattoo. Does everybody have their data dive tattoos? There's actually, this exact figure is right there in the raindrop. It's kind of cool. I just noticed that while I was sitting in the back row. This kind of gives a depiction of the statewide trend versus the trends of the individual land uses. So the statewide numbers, these are median concentrations, which are a good way to track trends. And the state numbers are in the bars, and then the individual land uses are the lines. And there is a statewide increase in the magnitude of pyrethroid detections at spot sites. And that's mostly driven by these big urban numbers. And the biggest points we have driving these numbers are places like Bouquet Canyon Creek in Southern California. So I've also depicted our Hyalella toxicity in the same way. Hyalella, I mentioned, it's an amphipod, it's like a little crustacean. It's a local animal of the California streams. It's epibenthic. It associates with the sediment. And about 1 in 5 samples are significantly toxic to Hyalella. And so these are the median survival numbers. The other numbers I presented in the map are percent mortality. This is percent survival. So there's a couple ways of looking at toxicity. And so survival goes up. That's usually good. And even though there's 1 in 5 samples that are toxic, sometimes the toxic samples are 0% survival, sometimes or 10% survival, and those are highly toxic samples. And sometimes it's just moderately toxic, maybe 60% survival or even 70% survival, but still an impact compared to a laboratory control. But over time, we've had this slow creeping up of our median survival numbers, and so there's a trend of increased survival over time or reduction in toxicity to high-level Azteca over time when the spot data set. Just a couple of other analyte groups that we measure. There's metals. We do legacy contaminants as well. A lot of things I'm not going to show today. But metals are showing an increase in urban areas and also statewide. We're really interested in measuring metals in spot because we're trying to look at reductions in copper at our spot sites because of the recent reduction of brake pad copper. Brake pads they're phasing out copper for use in brake pads, and so we're hoping to see a commensurate reduction in our spot sites probably by the early 2020s. Then there's contaminants that we only measure. That's interesting, the slide got compressed. Contaminants that we only measure at urban sites, things like hydrocarbons and the flame retardants, PBDEs. We're seeing a significant increase in PBDEs over time at spot sites. And there's another urban pesticide that we've been measuring for the last few years as well. It's called fipronil. And I don't have the data for that because I only have a few years of data, and we're not really seeing any kind of trend with fipronil just yet, but we are getting increasing numbers of detections of the contaminant. And we've recently added another test organism to try to account for toxicity that might be related to some of this fipronil that we're observing in the sediments. So this chironomous word should be more over here, over these bars, and the hyalella is represented in these bars. And so these are paired toxicity tests between our amphipod, Hyalella azteca, and this midge, Chironomus dilutus. A midge is a fly larva. And so there's sort of two different types of organisms, but both are aquatic, both are sort of epibenthic and associate with sediments, and they're both EPA test organisms for standard toxicity testing. And so our Chironomus test we started measuring in 2015 at only our urban sites. And again, this was the whole idea behind adding these Chironomus tests, was to link up the toxicity that we observed to any kind of fipronil concentrations, because Chironomus are more sensitive to fipronil than hyalella. And what's interesting is when I paired our urban-only hyalella results with our urban-only Chironomus results, we see this reduction in toxic samples. These are percentages of non-toxic, toxic, or highly toxic samples. We're seeing a reduction over these 3 years with our hyalella, but we're seeing the exact opposite with our Chironomus. We're seeing an increase in toxicity. So that trend I was talking about with hyalella survival improving over time, it seems like the opposite might be true with our Chironomus data set. And this is bringing home an important point about trying to look at the watershed with as many tools as possible to try to understand the health of the watershed. We're big believers in using suites of toxicity test organisms because they tell you what's bioavailable in the receiving system. Some other things that SPOT does that I didn't really talk about, but everybody can read about in our reports if you're interested. We're doing a lot of collaborations with the California Department of Pesticide Regulation. We have some extra sites that we monitor for them that track the reductions of pyrethroid pesticides as a result of label changes that took place in 2012. And we also just started this year to doing some water column testing with DPR's surface water monitoring sites. So we're trying to get at broadening SPOT's tasks to include some water column testing and to look at some pesticides that are a little bit more soluble and likely to be found in the water column. We're also doing monitoring of harmful algal toxins. We're doing microcystin in sediments. We have a few years of data for that, and we're hoping to publish a paper by the end of the year. We're continuing to try to investigate contaminants of emerging concern. things like fipronil are on a lot of CEC lists, and we're paying attention to those lists and trying to look at other contaminants that might be in the sediments. And then, as part of the last slide, I talked about having as many tools as possible to sort of broaden your perspective on your receiving system health. And we're very interested in trying to incorporate some of the newer tools like the bioanalytical tools and the non-targeted analysis, chemical analysis, to try to understand a little bit more the linkages between our dead amphipods and other potential impacts. And so we're hoping to have a pilot project come online for 2019 through the State Board, which will help us to expand SPOT's toolbox. And with that, I'll take some questions if anybody has them. Are we working with any kind of university extension programs? Our laboratory does a lot of work with UC Extension in the Salinas Valley doing ag stuff, but we haven't done anything in Southern California or beyond the Salinas Valley. But we'd be very interested in doing that. During expanding our monitoring to look at cannabis cultivation, we're working on another program in Fish and Wildlife doing cannabis monitoring, and so we are out there doing some downstream sediment testing from some grow operations that were illegal in Northern California around the Redding area. But SPOT isn't going to focus on that per se. We're actually pretty resource strapped, and this year we're actually reducing the number of sites we're going to try to maximize some of the constituents we can measure at some other sites of concern. But we wouldn't be averse to it if there was funding available to go there and start looking at legal or illegal operations.
It does seem sensible to being a new land that's coming onto our land.
Right. Now, I'm not familiar with how cannabis is going to get regulated in terms of how agriculture gets regulated, but if there's some chuckles in the room for those on the phone. But I'm just curious. I know Rich Brewer, who used to help with OEMA, is now doing some cannabis work with the State Board. So it'll be interesting to see how it plays out. But it sounds like it could be a significant land use. We might see agriculture increase in California if we include cannabis as a part of that. You have a question right next to you.
Yeah, so with respect to the mywaterquality, that's not necessarily taken up by water treatment plants. Those usually kind of tend to flow through.
Well, pyrethroids are really hydrophobic, and so for the most part, pyrethroids should get taken up in the treatment plants. But I know there's been some studies that show that they do get through, and they can get through at concentrations that can cause toxicity in laboratory organisms. But they're they associate with even in the laboratory, they'll associate immediately with the container they're in. You have to shake them off the walls of the container before you add your water to your exposure chambers. So that's just a unique. They're a unique class of chemicals in that way.
I'm just thinking that with the immense number of indoor cultivation sites we're seeing down in Southern California, we're seeing a lot of pyrethroids being flushed through the system.
Right. Yeah, there are other chemicals the question is, when we chose the sites, were we trying to consider sediment routing or looking for specifically depositional areas? That's a really good question. And when these sites were chosen back in 2007, 2008, each region had their input, and so these were sites that were important to each of the water border regions in California. And so a lot of sites that make perfect sense to a region didn't completely make sense in a statewide program, which is something that we're sort of addressing now after 10 years of looking at the data. When we go out to collect the sediments, we are targeting depositional sediments. We are looking for the finest of the fines. And, we scour a reach of not just a single point, we scour a reach at our sites, 100-meter reach. And, but we didn't consider, I don't think the deposition and the sediment movement within the particular watersheds was really considered in every region when the sites were first chosen. Some regions probably more than others paid attention to that. But the idea is that, the sediment is the transport mechanism for these contaminants, through the watershed as a whole. But we're more likely to find the contaminant on the fine sediments where there's lots of good organic carbon. So we're definitely sort of biasing the sampling towards these depositional areas. So the question is, it's a human health concern. Have we noticed contaminants that are related to human health, and has policy responded to that? And we're not really focused on the human health side of it in SPOT. We're looking more at the environmental side as like what's going to hurt the receiving system organisms. And the pyrethroid part of the story, that big highlight of SPOT, actually has been addressed, by DPR. DPR implemented some label changes in 2012 for commercial applicators that are like the orchid guy that comes to your house and sprays for your hands once a month. These guys used to have pretty free reign for how they could spray, and the new methods are very much constrained, to very small application amounts. And one of the things that SPOT's trying to do is see if that's made a difference. If you look at that first figure I showed about the trends, it doesn't appear that it has, but we're hoping to see the effects of that. And so there has been some response, in terms of what SPOT's findings. I should say SPOT findings have sort of fed into the information stream that led to that response from DPR. I wouldn't say it was all because of SPOT, but we played a role in that. But we're not really, associated with any kind of human health stuff. Probably the closest thing we're getting to is looking at the trends in microsystems. Great, thanks a lot.
Thanks, Brent. Thanks, Brent. Up next, I'd like to introduce Fraser Silling from the University of California, Davis. He's to talk to us about how we take open data and use it into open indicators.
Good morning, everybody, and thanks to the organizers for having me up here. I'm going to talk about, as Nick said, how we migrate from some of the things we've been looking at over the last few presentations and things that we haven't yet discussed about data that's accessible through different portals, and how we can bring those together in the context of indicators. This is an EPA Exchange Network project. It's in partnership with tribes and also the Department of Water Resources. So I did want to acknowledge a variety of people, including the tribes and the representatives of those tribes that I've been working with, and staff at California Department of Water Resources, EPA, and then there's people in the room who I've also communicated with about how we develop and use these kinds of systems over the last few years. This project didn't originate without a context. The context has been the evolution of indicators as a way of thinking about and measuring environmental conditions, economic conditions, and others in a way that we can interpret them, and we can convey large amounts of data in a public forum or in public fora or through public plans like the water plan and so that people can understand what we're talking about. And so that's the work of indicators. And but a really critical part of the work of indicators is that they are always based in science and data. And so that's the interface that we work at, is how do we take these massive sets of data and understanding about how these natural processes work and convey them in a way that's understandable to people. Sorry, there's a thing to trip on right here. So the partnership involved several important steps. The first was defining and describing and selecting indicators. So what are the things that are actually important to people? In the case of communication with tribes, they both talked about what's important to them and what they thought was important to the rest of the state. And so this was through multiple meetings with tribes, talking about water supply, water quality, environmental conditions, and drawing upon their knowledge. There's also, as most of you probably know, there's a California Water Plan 2018 update in process. So a lot of our work is associated with that. And also the 2013 update, which included a palette of water sustainability indicators. So I want to define indicators so that we're all on the same page about that. Our system is based on indicators, and these are intentionally selected in an open process. So they are open indicators, and they're intended to correspond to what our objectives are for natural processes, both in terms of what we want to get out of those processes, how we want them to function, to survive us, so a legacy effect, and also how we want to understand them. A lot of data that are collected are not understandable outside of limited groups of experts, and so we want to have that situation involved. They're also intended to be quantitative indicators. So these are quantitative measures. There are indicators that are subjective and very important in that way. In our case, all of ours are things that we can quantify. And therefore, they require data. So we need a supply of data and a clear and transparent way of evaluating those. I put some examples on the right. They didn't turn out so well on this projector, but the diagram at the top is the water sustainability indicators framework from the Water Plan 2013, and then the diagram on the right is a set of indicators for a Lower Sacramento River water quality report card. I should say that a lot of this comes out of different projects I've worked on throughout the state over the last 10 years. Okay, so the process we went through, we met with tribes, representatives of tribes in different fora, including the RTOC, which is an EPA collection of tribe EPA administrators. We discussed possible important indicators to them. There was some back and forth about how much they would want to share their own data, how much they could discuss things that they may be involved in litigation. This was true in the Klamath. It was true in Southern California over water supply and water quality. We also met with DWR staff and I've also met with State Water Board staff in various meetings, including the California Water Quality Monitoring Council, which I think is one of the most important vehicles for this kind of thinking. And out of this came a set of indicators. These are not all the possible indicators you could use. These are indicators that corresponded to those discussions, and they're also consistent with the Water Plan 2018. And so they're organized into three large categories and then a smaller category at the bottom: water supply, water quality, which is also related to water supply, and environmental quality, which is also related to water quality. So these overlap with each other to some degree, and they call up different things that we could have discussed already in this symposium, or that we might discuss in relation to change in depth of groundwater, or temperature, or nutrients, pesticides, and so on. An important aspect of this process is to take a raw parameter value and turn it into an indicator score. And this can be one of the more controversial aspects of use of indicators because it seems to be subjective. So what we try to do is remove as much of the subjectivity as possible so that when we give a score of 100 or 50 or 0, it relates to the natural process directly and the data for the natural process directly. So the process we use is to take environmental data. This is an old graph of San Joaquin River water temperatures from 2009 going through the delta. This is when you would expect there to be young salmon making their way downstream. And if that is indeed their window, they're just making it out before water temperatures hit this mortality temperature of about 25. And so this is around here is a cutoff for baby salmonids surviving. And then the temperatures down here are temperatures more related to successful recruitment of juveniles. And we can use these kinds of temperature relationships to survival with salmonids to develop a curve like this. So this is actually the curve we use to relate 7-day average daily maximum temperatures to an indicator score. And you can see it's not linear because the process is not linear, and I'll go into a little bit more of that later. Okay, so open data. Fortunately and unfortunately for us, there were a lot of transformations in state data in the middle of our project. So our original plans were thrown out the window with AB 17755 and the development of this huge range of, sorry, it's hard to find that. Do you know where the pointer is? To the front button. So there's a lot of resources, obviously, most of you know. There's CEDN, the California Natural Resources Agency has an open data portal. The feds have the water quality portal, and so there's a variety of data that we are drawing upon. And these come in different forms. Thanks. So the data are aggregated in a web system, and I can go into more detail with anybody individually in the break if you would like. Basically, we collect data from data sources, and they come in different forms. Sometimes they're spatial data sets, which is rare. More often than not, we're retrieving it through some process of where the data are made web accessible. So we have different collectors that schedule based on the type of data, the frequency of the data provision. So there are real-time sensors that we collect data from every 15 minutes, and there's other data that changes once a year, and so we don't worry about that one as much. All of these data are managed into a local and temporary storage location, which allows us to do our math, and then delivered back out through a portal. I should say as a caveat that my wish list, if I had Jay's wish list, is that we have a single portal for all water data in California. And I remember expressing that wish 4 or 5 years ago, and now we have several, and so maybe one day we'll have a single one if we all work on it. So we grab the data in different ways. Sometimes it's accessing through a query. If there's a fixed query, so WQP has a certain query structure you can use, a URL structure that allows you to grab the data. Fortunately, the state agencies have been setting up very friendly devices for us to access data, and so we can develop a standard script to pull the data. And there's actually some data that we can't do that, and so maybe it's produced in an online table, which we scrape, very technical term for kind of spatulating the data off the website into a repository, but it seems to be pretty effective when there's not another tool. And then we work on visualization. This is all of the water diversion points in California. I think there's 40,000 or so, and about half of them have recorded water uses. So there are water diversion rights that don't have reported use in recent history. Those are in pink, and then the green ones have a recent and recorded water right pull with the State Water Board. So this is an example of a visualization. I'm just going to go through examples for now. And so you can zoom in on a map like that, like all of these kinds of portals, they work in similar ways. In this case, pick a dot of one of the diversions and find out its history. That could be in the case of water diversion, we only have data back a few years, but you could also look at, this is its monthly water diversion history, this is annual water diversion history. And also we, similar to the HAB website, set up so that you can pull the data yourself. Based on the spot you're on, you could pull the data as a CSV. Depending on the type of data, you might pull it as something else. And then so that's data organized by say, an indicator, or in this case, a raw data source. We also have the data organized by regions, and these are different scales of watershed, HUC 8, HUC 12. And you'll see that some of these are individual points, and they're far enough apart that they're not clustered, and some of them are clustered, and they have a number in the middle, so that's a 7 in the middle of that blue blob. That indicates that there are seven nearby points. And so regions where we're looking at watersheds, and we're also looking at aggregating them by their proximity along a water body, which would then allow you to group monitoring stations or wells or things like that and pull all the data together or see all the data together. So this is an example of how the indicator conversion is done. This is based on now fairly old information about the relationship between water temperature and growth and survival of salmonids, and then taking that temperature information and turning it into that score curve that I talked about earlier. And so in this case, it has a particular formula that describes that curve. This is an example of one that's not linear. There's other things that have linear relationships between the raw parameter value and what you might give as an indicator score. And then there's different temperature cutoffs you could use for instantaneous effects versus long-term effects when it comes to something like temperature, or it could be a pesticide as well. This is an example of what the corresponding map looks like to the indicator conversion. So all of these points are surface water monitoring sites, stations. The color red to green is the temperature value. So green would be a score of 100, which means a healthy temperature for salmonids, and red is a score closer to 0 to 20, so it's an unhealthy temperature for fish for all the last data points in California for all the stations that were available. So this map was created 2 to 3 days ago. So these data could represent that day's information, or for some of these sites, it's older, and so it's less relevant from a contemporary point of view. But this gives you an idea of what a product would look like. Obviously, you can zoom in, and then you'd be able to click on an individual monitoring site, see how the temperatures varied across time, and also retrieve the data for that particular site. And one important thing is that we are looking at both surface and groundwater, and that's from both of our other partners, the various tribes and the Department of Water Resources. And some of these are going to be data associated with wells, and so these are wells with data. The white dots, the black circles are wells with data that we would use. But some of it's also derived data. For those familiar with the groundwater monitoring and modeling by DWR, they put out some nice products in raster form of modeled changes in groundwater depth, and so that would be something that we are also including in the web resources. And then there'd be something like a water quality attribute like nitrates. Nitrates are important in surface water and in groundwater. They mean different things in those different places, and you might use a different relationship between the raw value, in this case is the drinking water quality indicator curve, so indicator score of 100 is for nitrate values of less than 9 milligrams per liter, which is a background nitrate concentration determined from a study a few years ago in the Central Valley. So if your concentration is below that, then your score is 100, and if you're above the toxic level for drinking, then your score is 45. And so these are all of the corresponding indicator scores for the nitrate values. In this case, it was the most recent. I think most of these were in the same time frame, and this is from a couple of years ago. Okay, so our next steps. This is actually a project that's not quite done, unfortunately. So we are still in these steps right here, finalizing the data collection process, and so we have that done for about half of our indicators, and also the equivalent score calculation. That's done with different R scripts and other scripts in the background after we've collected the data through the collector mechanisms. We also are associating sites with each other, and that could be that they are along the same NHD flow line or within the same watershed, so that people can aggregate sites of interest. And then communicating with stakeholders, this is what we found out and what do you think? And we have to finish up in the next 3 months. So that's our status. One of the things that, among other automated features, one of the things that we're really interested in is including things like really good trends analysis using the statistical package so that we can say whether or not things are going up or down. If you would like to contact me, especially if you want to be on a list of people who find out right away that the website is done, or if you want to check it out when it's almost done, please feel free to email me and we can have that conversation. Thank you very much. Questions? Yeah. I'll read into your question. We have, I think, two kinds of audience. One is our scientific or technical audience that says yes or no, this is good or this is worthwhile, and the other is a broader, less defined audience for indicators. In their confidence will come from, they can see a provenance pathway. It comes from the university. We have partners in agencies and tribes. We have retrievable data so they can do their own calculations, and so building confidence through that transparent process I think is really critical for people to understand and use indicators of any kind, including through a web portal. And then confidence in the back end, there's for each of our score conversions, they have their own provenance pathway of why did we choose that method. And also again with the anybody can retrieve the data that went into that. They could do their own calculation with a different set of rules and say, no, I don't agree, or yes, that sounds good. So consistency with current scientific knowledge is the other kind that cover the spectrum. Okay, thanks. No, I'll repeat the question. Do we have difficulty removing duplicates? So yes, fortunately, the state and Fed resources have thought about that, and so we have some crosswalks in terms of coding station IDs, which is the easiest one to deal with. The less easy one is geospatial location, because obviously there are state agencies that have used USGS locations to do additional monitoring, and so you have geolocation, but separate tasks, right? So we face this with other stuff we do, automated tasks where you want to look for if you geo-colocate and temporally colocate and parameter colocate, maybe you only need one of those. And so that's our cutoff, is not necessarily to include everything, but to parse out the representative of that event, which is that date, time, space combination. Yeah. But yes, it is difficult. Another question. It's likely that those curves will change with change in knowledge of how systems respond to environmental conditions, or in some cases these are legal or regulatory standards, and so those can also change. So for example, for arsenic and nitrate, they've changed, and changing for mercury, and so there's different regulatory standards that would change, usually in response to new knowledge and new data about how systems are responding to contaminants or physical conditions, et cetera. So yeah, I expect that those would change. Yeah, so that's a perennial problem, I think, when you do these kinds of conversions, and there's two solutions. One is that you know that the past map was done using a different method, and the other is that you retransform or transform the previous data with the new rules, which is how we're doing it, so that your presentation of legacy information is always based on your current knowledge. So I feel like that's the best of an imperfect set of solutions, is we say, if we had done this 10 years ago, we'd have this map, but since our system is automated and always updated, then it's always based on our current knowledge, which isn't perfect, but it's what we think we know right now. Yeah, and that would be, I think, it's not hard to do with an automated system. This is intended to replace something that I've done for years, which is a expensive desktop intensive kind of process, which has very low transparency. And this provides that, it takes it out of my hand, so to speak, and says, here's all the legacy data, here's the conversions, here's how they were done. And then what you're talking about, you can archive that knowledge more easily and in a way that people can access it. All of my previous projects that cover about half the state are on my computer and you can't see it. That's not a good situation. So this allows for that, all that legacy and provenance pathways to be accessible. All right, thanks everybody. Hope you enjoy your break.
Great. So we got about a 20-minute break. I encourage you guys again to network with each other, follow up, exchange contact information, and reconvene at about 10:45. Thank you. Break, had a chance to look at some of those posters and network a bit. Up next, it's my pleasure to introduce Pete Odie from the Department of Fish and Wildlife, who'll be talking about our bioassessment program.
Great. Well, thank you, Nick, and thanks for your organizing this, Greg, and all the OEMA folks for making this happen. It's great to be here. I'm going to talk today about the theme of this symposium from the perspective of our bioassessment program. I think most of you are familiar with bioassessment, but I'll start with the definition anyway. Bioassessment is the direct measure of aquatic ecosystem health from the organisms that live there naturally. So this could be fish, invertebrates, algae, riparian vegetation, et cetera. Lots of different things that we could use as indicators of that. There's a lot of interest in using these types of indicators because they integrate a lot of the information that we're interested in. So they respond to many different types of water body stressors, and they integrate impacts over time and space, particularly throughout a watershed. Now, the SWAMP program has been putting a tremendous amount of resources into this program over the last decade, and we've seen the benefits of that. The program now has greatly expanded the technical rigor and the capabilities of the state to be able to use this type of information. We have standard methods for field and lab data management, quality assurance, et cetera. We've got multiple indicators that we've been developing. Benthic invertebrates, benthic algae, riparian vegetation are pretty well established now. We're also looking at new and experimental indicators for multiple fronts as well. And we're also looking at using these techniques across different water body types. You know, wadable streams was where we began, but we're developing these techniques in other areas as well. Another area of focus is what we call causal assessment, which is the process of figuring out what's wrong if you've got biological impairment, what's the cause of it, what's the source of that. The final thing that area of focus for us has been taking this type of information, this biological integrity information, and using it to help us set targets for policies that we're interested in. So things like hydrologic alteration, habitat integrity, nutrient enrichment, et cetera, are some areas that we're actively involved in. And if you think about the theme of our symposium, this type of information is really helpful. It's like having these types of indicators available will give us a lot of assistance in helping us manage our aquatic resources in the face of the kind of changes that we're anticipating and experiencing. So you can think of our program as essentially building a baseline of information. We have really massive data sets, sampled several thousand sites around the state now, and we have a lot of really good data from these. Calvin's going to be talking about our reference and perennial streams assessments a little later, so I'll let him, won't steal his thunder on that one. But this data set allows us to do a lot of interesting things. expectation and its causes. So that's sort of how our program is set up. So that gives us a basis for quantifiable, objective detection and prediction of impacts of disturbance. So if we want to be ready to deal with change as it's happening, these are the kinds of things that we need. So I'm not going to talk about this, though, anymore. This is not what I came here for. What I wanted to talk about was our vision. And I gave a similar talk, or a related talk, I should say, at the Detroit Freshwater Science meeting. It's called California Dreaming. And we, started by singing the first few bars of the song. I was going to do that today, I thought I'd spare you. Didn't go over so well. So our vision, let me just read this to you. This sort of encapsulates what the program sees as its goals. Measures of ecological integrity are fully integrated into California's natural resource management programs, and California prioritizes this information to protect and restore its water bodies and watersheds. So that's the vision. And I've spent a lot of time thinking about this over the years. We've been working on this stuff for a couple decades now. And we've spent a lot of time working on the technical pieces, and we've developed a lot of good science. But we have talked a lot with my colleagues about this over the years. I'm impatient, right? Why has the transformation not happened yet? Why are these types of informations not, driving the ship in terms of how we assess and measure our condition? And I think that we have to ask ourselves, if we continue, to focus strictly on developing the technical tool set, developing the ability to do this well, will we get there? And I think the answer is no. I think there's another significant challenge that we've got, is what I'll call our non-technical hurdles. And that it's really focused on this issue of making this information easier for managers to use, people that need to use this information. And so if the vision, so maybe the way to think about the vision is that ecological data are used to make better decisions, we need to figure out what's limiting that and how do we help that. So we think that success in this area is going to require us to think about water body health at multiple spatial scales. This is something that ecologists are trained to do. It sort of comes naturally. Because it requires a search for patterns, patterns that occur at different spatial scales, and learning how to look at that. But we don't have very good tools for communicating this with managers. And so our program has been shifting some of its resources to start to develop some tools to improve this. So that's what I'm going to talk about for the rest of the time here. Now, I'll start with an example. Well, let me just back up. So there's two types of things I'm going to talk about. One is what I'm calling tools that will help us interpret data within a spatial context. And the second is tools that allow us to integrate ecological data with other information about environmental health. So in my first example, I'm going to talk about spatial models that we use to extrapolate bioassessment scores to unsampled reaches. Common question that we get is, well, I've sampled these sites, how many samples or sites do I need to assess this stream? When do I know when do I have enough information to make an assessment? So the approach that Rafi and Marcus and some of our colleagues have been working on is to develop these models called spatial statistical networks that are used to estimate scores at unsampled sites based on spatial relationships at sampled sites. And so here's an example of that. This is a stream network from Malibu Creek. The network here is replaced by dots, essentially at every kilometer in the whole stream network. And these are essentially predictions of CSCI scores. CSCIs are benthic invertebrate stream health index. And so it ranges from 0 to a little over 1. If you're at 1, that's considered healthy. And there's a threshold somewhere below there that you could set. And so here the dot color corresponds to score. So oranger is worse and greener is better. And the dot size corresponds to how confident we are in the prediction at that location. So a bigger dot means we're more confident in the prediction. So if you use this, you can use patterns in these kinds of outputs to describe the confidence that we have in assessing the biological condition throughout the network. So for example, we could say for regions that have a lot of, say we're very confident that regions are failing to meet objectives like these orange ones, we could use that to prioritize restoration in those areas. Conversely, in areas where we're pretty comfortable saying that they meet our objectives, we can prioritize protection in those regions. And then for areas where it's uncertain, we could prioritize monitoring. So it's a way of putting this information in, condensing this information and making it easier to talk about. So, second example is what we call landscape models that we're using to identify areas where biological integrity is constrained by development. So we know, if you spend any time in the state, we know that there are certain regions of the state where high biological scores are just rarely, if ever, observed. They've been so altered that it's difficult to see high integrity. It's because pervasive alteration in some of these systems constrains biological integrity across a whole region. And some of these constraints, can't be overcome with our current management tools. These are things that, even if we tore out all the concrete or completely altered the landscape back or let it be back to what it was, it might take, generations or more before some of these systems no longer see the impact, the alteration from that. So, but we still want to use ecological data to assess these systems. I think that's the key here. So if we're going to do that, it's helpful to understand, describe in a objective, systematic way where these are. So these models came out of that drive to get an objective way to identify those. So the approach here is to build empirical models that predict ranges of expected biological condition scores for each segment in a region. And we're using some great resources that came from the EPA, the National StreamCat database. Gives us data now that we can grab and use for this. So the kind of output that we get from these models looks something like this. We can classify a stream network. Here I'm showing for the whole state of California, but you could do it regionally as well, and we in fact do. And using different inputs and then criteria, we can define different stream segments as either constrained or not constrained, or likely constrained or not likely constrained as we choose to. So it gives us again an objective way of doing this. And we can play around with this. We can play with the thresholds. We can play with the inputs. We can play with some of the thresholds that we use. And so the value of this, or some of the values of this, is that it allows us to look at patterns of predicted condition across a region. So we can do that, with our observed data. So we compare what we predicted to what we see, and then look for over and underperforming areas, and then look for patterns in that. Is there something related to this portion of the watershed that's doing much better than we thought it would, or much worse than we thought it would? This is really especially helpful in areas that we don't have a lot of monitoring resources or haven't put a lot of resources into it. There's also a direct biocriteria application because we can use this type of information to estimate the extent of streams that are not likely to meet certain criteria. And that's really helpful in our stakeholder discussions, as Jesse well knows. So in fact, that's where a lot of this work came from. So I'm not going to talk about this anymore. There's a lot to this. Marcus is going to be presenting right after me about this in quite a bit more detail. So a good example of this. Okay, so And I want to finish with something a little different this time. We've been working on tools for integrating ecological data with other environmental information. And a lot of people have been doing this. There's a lot of interest in synthesis now. You just heard Fraser give some great examples of this from his end. He's been working in this area for a long time. And so have others. A lot of agencies are now grappling with this problem that we've got a lot of environmental data now. But it's overwhelming. There's so much coming in, so many different forms of it. We need a way to use that intelligently, put it together in a way that we can use to make good decisions. One point that I'd like to make here is that I think if we're going to do this well, we need to communicate not just within our own agency silos, but it's really essential that we work across agencies or across entities. I tend to, because I do a lot of work for the water boards, I tend to think in terms of the Clean Water Act, and I think a lot of us do. But the partners that we need to work with don't all speak Clean Water Act. It's not what they all start their presentations with, the Clean Water Act language, So I think it's important to realize that. So here's an example of a partnership that does along these lines. So the Nature Conservancy has been working on a project they call the Freshwater Conservation Blueprint. And this is a highly collaborative effort amongst a lot of different agencies and entities. It started when Jeanette was working on something she called the Freshwater Biodiversity Mapping Project. So she assembled a large team of experts in different biological fields to create the first ever maps of freshwater biodiversity in the state. So she brought together fish experts, amphibian experts, the bug folks, and even birds and mammal people. And these integrated some of the best available information we had and used that to put together distribution maps. So this is just one example of what came out of that, is just diversity maps of where we have high levels of diversity, endemism, and vulnerability. But there's lots of other details in there. But this is the kind of thing that came from that. So that was essentially phase one of this larger project. Phase two was to take that information and use it to identify a network of what they call priority watersheds, based on representing that biodiversity, capturing, making sure that that's protected. And so this framework then was really helpful in communicating with wildlife and fisheries entities that are already thinking about some of this stuff. The third phase of this project was to take that information and combine it with information about vulnerability, climate vulnerability, and other types of development or projected vulnerability to inform conservation strategies. So the idea here is, if you have this information, how would you use it to identify areas that need protection or restoration or monitoring? And so that type of structure has been, I think, the kind of thing that we need more of. So I started with this idea of this vision and what's missing. I think we tend to focus a lot on the technical pieces, and we will continue to do so. It's critical that we have good science behind our assessments and our measurement of the stuff. But it's just important that we spend time on this second piece. I think that's my plea for today. So I'll just finish. This is a really wide and expanding group of people that we partner with in one way or another, so I just want to acknowledge them. Bryn Zabaloni's in there somewhere. There it is. And just some special thanks to a few people that did some of the technical work on this. So, thank you. Any questions? Any questions? Yeah. Well, it's important, I think. The question was, how do you balance this idea about integrity or biological health and integrity with economic reality, socio-political reality. Well, I think one thing that's missing from the discussions I've heard on this is that I think that we as scientists do a really bad job of, and I heard this yesterday, about converting these values that we have that are implicit in the kinds of tools that we're developing in terms of monetary value. Because a lot of these don't really have monetary value. They're not easily converted into that currency because it doesn't really work that way. There's a lot of these are social values or socio-political values. In terms of environmental justice, a lot of these areas that we're talking about protecting are areas that some people don't really have the resources to ever experience. I guess that's a long-winded way of saying I have no idea how you communicate it, except that the only stab at it I can take is that I'll start with what I began with. Is I think that we need better ways of translating what we as ecologists do intuitively, which is think about spatial pattern. I think that people respond pretty well to that. People respond to maps. So I guess that would be my starting point. but part of it is just not lack of awareness. Some of it is, just not aware that these tools are out there. The second is trust. I think that this is sort of implicit in what, or explicit in what Steve said. I think we have, the people who work with these data a lot have a pretty good sense of what the limitations of our understanding are, and also some of the, like the constraints we talk about explicitly here, that we don't really think biology is going to score higher than this. But if our regulatory frameworks are one size fits all, there's a frustration, I think, that we're expecting people to meet a standard that maybe isn't, appropriate. And I think that having a way of talking about this in a way that's objective and defensible and not just, reactionary, can help that discussion happen. So there's, maybe some more trust between the parties involved. But yeah, I've talked for a long time. Thanks, everybody.
Thanks, Pete. Up next is Marcus Beck from the Southern California Coastal Water Research Project, following up on Pete's talk.
All right, good morning. Well, I hate to break up that really great discussion, but I think what I'm going to talk about next is really relevant to these really tricky issues with how we sort of prioritize given lots of information and different ways of allocating different resources. I'm Marcus Beck. I am a relatively new employee at SCORP, and I know that a lot of you are familiar with SCORP and what we do, but we are a research organization that I think sits in this really nice spot between science and the people that want to use it. So we are a joint powers authority that basically works with various institutions and agencies in the state to give them science to help them better achieve their mission. So obviously a lot of what we do is science translation in a way. So putting the tools in the hands of the people that are actually going to use the information to make decisions. And this, what I'm going to talk about today, is a great example of that. Basically, in a nutshell, how do we use bioassessment data, all this information we have, relative to the context that you're working in? So as Pete mentioned, these sort of landscape constraints that are maybe putting potentially unreasonable expectations on what you might achieve at a particular location. So again, the technical side of this, very well developed. We have, at least from a stream perspective, the reference condition issue taken care of. The CSCI bioassessment tool is very well developed. So we're in a situation where we have all this data statewide, but how do you use this information to actually better manage these individual locations? We know what the condition is. How do we apply it? Obviously, in a perfect world, low-scoring sites, we want to improve them. High-scoring sites, we want to protect them. That's as simple as it gets. But based on everything we were just discussing right now, in reality, we have limited resources. We can't manage everything. Every site has a particular context that we have to consider. And in a lot of cases, particularly in California, these heavily urbanized areas, or even these agricultural areas, there's these so-called, unmanageable stressors that really place upper limits on what you might expect to achieve at a given site. So we need to start thinking about, how we're using these bioassessment data, how do we apply it at a watershed scale to basically develop solutions given problems that are measured at a particular site. So these needs, these management needs and how bioassessment is used must be defined in a regional context. So this is the problem in a nutshell. So how do managers use this information? So this is an example where, from top to bottom, these are a bunch of stream reaches where we have bioassessment scores, CSCI scores on the x-axis, and then this sort of biological objective threshold that we've decided to use for what's a good or bad score. So if you're a manager and you look at this information, you might say, okay, well, there's these sites right here that are right below my biological objective. Those are the ones I want to focus a lot of my effort on in terms of, maybe doing some restorative measures or, more monitoring to figure out why and how to get those sites back up above the threshold. That's great, but then you think about, well, we don't have all the information at play here to fully interpret those sites. We need a context to interpret what's possible, what's the expectation at those sites relative to regional constraints that might place upper limits on the expectation. And so this model that we've developed, this landscape model that Pete was talking about, does exactly this. So we have these observed scores at our sites, and then this model gives us a means to place bounds on an expectation that site is likely to achieve given these large level constraints. And so now, we can look at a place like this and say, okay, we know that this site is below the threshold, but it's expected to have a range up here. So if we focus our efforts on this site, we are probably likely to achieve our goals to getting that site back up to par. Places like these that are, still below the threshold, maybe it might be impractical to really put in a bunch of resources to try to get that site up to par, because we know that there are some pretty high level constraints on what we expect to see at that site. So this is a prioritization tool defined by context. These models are great. We also want to combine them in a way that sort of really leverages data visualization to help bring the tool to the managers. And I'm actually going to be on the panel later talking about the tool that we developed to do this. But again, the context is these developed landscapes and how to sort of identify these locations where watershed development is really maybe limiting what is likely to be achieved for a bioassessment score. So we can use these models to do that, and we can incorporate them in a sort of data visualization framework to really bring the models to the people that are using them. So if I had a lot of time, I would really go into the nuts and bolts of how we develop these models, but long story short, we're basically using, for every reach in the state, we have a measure of watershed land use. We're using measures of urban land use cover, agricultural land use cover, and modeling CSCI bioassessment scores as a function of those variables to get an idea of not only what the most likely score is that we might see at that site given the landscape, but also what the ranges of scores we might want to see or we're expected to see as well. So we're using random forest models, but also quantile random forest models, which gives us the ability to get a range of expectations around that central tendency as a function of landscape. So we did this for the entire state. So for every reach, we have this range. And what we can do with this range is, and then this is where sort of the rubber hits the road with this model, these are sort of 16 hypothetical reaches. For each reach, we have a range of scores that are expected given what's going on in the watershed. And we can basically sort of pick a bound of uncertainty around those values to say, how certain are we in the model, or how narrowly do we want to define that context, and then overlay that with potential biological threshold. So this is showing us really kind of 4 different classes of constraints that we can define from the model output, given how certain we are and the range of scores that we're seeing, and how that certainty value overlaps with a threshold we might want to use to define what a good or low score is. And so sites where reaches where the range of scores don't overlap the threshold and are well above that threshold, we're calling unconstrained sites. These are sites where we're not likely to see constraints from land use development. So those sites are expected to score higher than, say, their opposite counterparts on the lower end of the spectrum, where their scores are well below, the range of expected scores are well below that threshold. And then we have these sort of intermediate categories that are sort of variations on a theme. So this is sort of this intermediate category where we're saying these are more possibly constrained or unconstrained, because they're sort of closer to that threshold. So anyway, we have these classifications that define the expectation for a reach given what's going on in the watershed. We've done this for the whole state, and Pete showed the same figure, but these are sort of mapping out those 4 classes for the entire state. And this is sort of showing the breakdown of the percentages of those classes that we see. Actually, this should say likely unconstrained. But the point I want to make here is this follows patterns that we exactly expect. So places where we have a lot of landscape pressures that might be placing limits on biological condition, like the Central Valley, South Coast, so ag urban areas, those are places where these are, there's a high prevalence of constrained sites. On the other hand, these more pristine areas are on the opposite end of the spectrum. So this is good, but again, where we really want to go with this is putting this model in the hands of the managers to make decisions. Having something at the statewide level is good, but how do we scale it down in a regional context to really help prioritize? So we did this for the San Gabriel River watershed. We worked with a local stakeholder group to help them not only understand the model, but also apply it to the issues they had in their watershed. So this is the land use in this watershed. This is a really good example of a bipolar watershed. So, no development, and then LA happens. And just as an aside, this is my second time in Sacramento. Both times I've flown up here, I've caught the night flight from Orange County up to here, and I'm always amazed flying over LA at night. It's absolutely nuts. But at the time I flew up here on Monday night, I was actually looking, I could see this watershed literally, and there's Christmas lights, and literally this line where it stops, and then there's just nothing, or in terms of urban development. So it's a really good example because managers in this watershed are struggling with all of these sites in the lower watershed where they have all these bioassessment scores, the sites aren't performing well. How do they manage those given the context that they can't, tear up asphalt or remove engineered channels in a way? So how do they prioritize given what the potential ceiling is? So to help them do this, we took the landscape model, integrated it into a interactive online tool that they could use to, again, not only understand the model, but use the results to prioritize actions for all of the sites in their watershed. We're calling that SCAPE, the Stream Classification and Prioritization Explorer tool. It's online, you can see it. It's actually specific to the San Gabriel watershed at this point. But everything I'm going to show in the next couple of slides are things that this tool will let people do. So you have maps to see the results. You have sort of a tabular summary of what the scores are relative to the expectation, and then where the rubber hits the road, we have a way for them to help prioritize the actions based on what they're seeing given the context. So we had a lot of discussions with this group in terms of what management priority is for their region. And after a lot of deliberation, we basically came down to 3 rather generic recommended actions that could come out of this tool. How the site is scoring relative to the expectation. What do you do with that? So they said, I'll go into detail about how these might be mapped to those expectations, but what you see from the model, they're going to say, okay, we want to sort of prioritize things by maybe we want to do more investigation. Why is something scoring above or below the expectation, for example? Maybe we want to implement some sort of protective actions. So things that are high-scoring sites, they're likely unconstrained. Maybe there should be more scrutiny, if you're going to propose a project that might impact that stream. So that's sort of protect. Then there's restore. That has a pretty clear meaning. If something is scoring below the expectation, then you want to get it sort of back up to where it should be, given the landscape. I should also mention that all of these scores are in addition to what we're calling routine baseline monitoring and management. So this is extra actions that are on top of what's already going on. So the fact that maybe we we don't assign an action to a place doesn't mean we're ignoring it. It just means what we're already doing is okay. So we gave the stakeholder group this figure to help them sort of understand all of the ranges of possibilities you could get from the model. So these are 16 possible scenarios you could get where the circles are the observed CSCI scores at the reach, and then the ranges of scores are the lines there. So we have situations where a reach could fall in one of these 4 classes, but also for any given reach, the site could be scoring above as expected, under, or under and below the threshold, and all the derivations in between. So these are all the possibilities that could come out of the model for their watershed. And they wanted to basically say, for every one of these possibilities, what sort of recommended actions might we want to do to help us prioritize, given that we can't do everything everywhere. This is what they came up with. Same plot on the left, and these are our 3 decided upon management actions. And so for all of the scenarios, they wanted to say, among these 3 actions, how do we rank them from high, medium to low priority within the context of the observed score relative to the range of expectations? So a lot of this makes sense. A lot of the stream reaches that are likely unconstrained were ranked pretty high for protection. Things that were either underscoring or overscoring relative to the expectation were given typically an investigate category. So why were they behaving that way relative to what the model was showing? Things that are consistently either below the threshold or scoring below the expectation were typically assigned a restoration action. But the point being, this gives them the ability to sort of parse out all of the possibilities and also rank qualitatively from high, medium to low, given that some places your management actions may or may not have the intended outcome given the constraints. So this is a really cool part of the app where the map shows them the scores relative to the stream reach. So we have arrows showing underscoring or overscoring, circles showing as expected, and then the reaches are color-coded by all of the reach classifications, so likely, possibly, constrained, unconstrained. And then we said, so this table right here, or this figure table, we let them sort of, the app actually has these drop-down menus where they can assign the different priorities to all possible combinations. And how that propagates in the app is you get these maps that show where these recommended actions are on the landscape. So it's a decision tool as well as sort of a visualization tool to see, of the decisions you've made, where are they falling out in the landscape. So, again, the investigate categories were, ones that were over or underscoring relative to the site. So I remember these ones up here these are actually underscoring sites on the east fork of the river in this largely unconstrained region. So they said, we want to know why those are not performing as expected. Similar to down here, I forget exactly what, these are actually, these 2 are overscoring sites for these constrained reaches. So why are those guys performing better? They thought it was important to figure that out, given that it was a constrained region. These are all the protect sites. So again, most of the sites that were scoring as expected in these unconstrained areas, they said these are probably pretty important just from the perspective of the natural biology of the region. So we want to put some protective measures there to make sure that they stay that way. And then finally, this is probably the most sort of controversial part of this. So the restore sites, speaks to all of these sites in the lower watershed, where they said, we recognize that these are really highly constrained areas. We don't want to ignore them completely, so we're going to say, we want to restore them, but we're going to give them a relatively low priority, so they're the smaller gray circles, because we know that it's going to take a lot of effort, or maybe even impossible, to really restore those sites, given that there's these large-scale landscape constraints and possibly even a legacy impact if we were to theoretically remove all of LA. So we're not ignoring these, but we're giving them a low priority because we know it's just going to take a lot of time, or might not even be possible. So that's the model in a nutshell. Obviously, this is one approach to a very gnarly topic. How do you sort of prioritize with bioassessment? But we want to basically emphasize that really at its heart, this is just a discussion tool. It's a way to spark discussion about how do you spend limited resources using bioassessment tools to guide that process. And we think this does a fabulous job to help facilitate that. So it's a screening tool at best. It's not a tool meant to create a regulatory designation. It's not meant to do that. In particular, it's not a tool that can be used for use attainability assessment. So it's not something to sort of think about, how do we redefine these places to give it a different standard? That's not what it's for. It's an associative model, so it's not used for causal assessment. We're linking in-stream biological condition to landscape development. So that's a whole pathway that requires disentangling for really diagnosing what's the cause of degradation at a particular site. We're just trying to predict the biological condition. We are not trying to identify where modified channels have occurred. The fact that all of those sites in the lower watershed, 90% of them are probably engineered channels. The fact that they're showing up as constrained is not because they're engineered channels, it's because the landscape around there is developed. So this is sort of just a correlation. There are much better ways to sort of identify when and where channel modifications occurred. Yeah, so that's pretty much it. It's a discussion tool meant to prompt a different way of thinking about priorities. We think this is really valuable. It gives a context to managers that they didn't have previously. More importantly, the link to swamp data is, as I started this talk out, we have lots and lots of data available to us now, and how do we sort of synthesize that information and help managers use it in a way that helps them do their job better. In other words, more informed use of limited resources can be derived from this tool. I will say that because the model is developed for the entire state, we can apply it to other regions. But again, the context of how that model is applied to different regions depends on the needs of the local stakeholders. So we worked really closely with the San Gabriel River folks to help them understand how the model works, but within their region, what needs they have and how the model can help inform those needs. So if you are to apply it elsewhere, just realize that you've got to work with the local people to understand what their issues are, and that the priorities we have here might not apply. So I would love to, if anybody wants to apply this elsewhere, give me a ring. I'd love to talk to you about that. So that's our approach. Again, I'll be at the panel discussion later, and this was definitely a collaborative effort among not only my co-authors, but the folks at the San Gabriel River RMP. Great help, working with them and understanding their needs. And we hope it's been helpful for them, and we hope it'll be helpful elsewhere. So I'll take some questions.
How common is it for sites to overscore relative to prediction? What sort of factors do you think are at play when that happens? And does that cause you to revisit and usually remember?
Yeah, so the question was, how common are overscoring sites, and do we have a means of sort of understanding why that has occurred? Is that more okay? So we are actually working on a paper right now that describes this, and we have a section that sort of tabulates that out. It's actually it's very similar to the statewide distribution of just the constrained classes in general. Most of the places are scoring within the expectation. So the ones that are over-underscoring are kind of in the minority. So that speaks to kind of the prevalence of that. But in terms of the reasons why, it could be any of a number of reasons. Again, this is a model that just is a function of landscape development to biology. It could be anything along that pathway. And so that's why, when we're working with the stakeholder group, we had that investigate category. They wanted to know why that was happening. And so we have these, the way we've described that category was, well, looking at additional data, looking at other monitoring data, going to the site to see what's happening. So this is an approach to help you answer questions like that, but it doesn't give you the answer. It's a starting point. So that's all we can do right now.
Coming from a previous perspective of the Delta, and you already kind of gave yourself all the caveats about regional specifics, but ag can be different, particularly depending between annual and perennial crops. And so I know every time you put another bin in the system, it complicates things, but I don't know to what extent the difference between, a vineyard or an almond farm or something like that between an annual crop and how that might play different in their land.
Yeah, so the land use issue and what's driving the model was a big point of discussion we had when we were developing this. So what variables do we include? We used the StreamCat database that's like 100 some odd variables at the riparian, catchment, and watershed scale. A lot of those variables are a lot of things in the same theme, so urban development, ag development, and they do sort of parse up sometimes, to different crop types. But again, we did have a lot of discussions about that, and we found out that this model works really, really well in watersheds where you have this big urban gradient, as well as ag gradients. Beyond that level of specificity, we can't really say at this point what's driving the bus in terms of different types of land use. I will say, though, that speaking to the issue of applying it to other regions, the model had the most poor performance in areas like the North Coast region and the Sierra Nevadas, because there's not strong, at least relative to the South Coast or Central Valley, there's not strong urban gradients there. And that could be, we're not, this model doesn't necessarily capture the relevant stressors for those regions, like legacy timber harvesting. I don't even know if there's data available to fully describe that at a level sufficient for our model. But the issue of what variables we're putting in and how the model is interpreting that and how the user interprets that is something we've discussed at great lengths. And it's, at this point, in terms of moving forward, that's definitely something we're going to explore more. So.
No, okay. My name is Tony, and I think it's great what you guys are doing. I do often think, though, about the ways that we might be including certain assumptions into our models that may have unintended results. And in terms of what we've shown here, one of the things I do worry about, and this is, I think, in line with something that Fraser said earlier, is that sometimes the heavily constrained areas might also correlate to areas where there are disadvantaged communities. And in terms of the way the priorities are set, it seems like there's the risk, at least, that those that rank low in terms of being a highly constrained area might also then have the correlated effect of having less investment for restoration. And I just wondered if you've had any discussions with, let's say, DJ groups or other interested groups who might want to kind of understand how that model.
Yeah, so I'm going to try to paraphrase that. So the question was the issue with constrained areas, urban areas. We haven't looked at this, but your point was they correlate oftentimes with communities that are less opportune than other locations, and we haven't had those discussions at all. And I remember that came up yesterday with someone's talk. And I think the issue is kind of related to, the chicken or the egg. Is it because there's, these are more poor communities, they don't, that's why the stream is degraded, or it's because these are areas where there hasn't been investment, that's why the stream is degraded, and therefore that's where these communities tend to land. we haven't even begun to think about that sort of complex interplay and how these models were used. But I think it's more, I don't want to pass the buck, but the stakeholders at the watershed level, that's something that they, I think, need to think about in terms of how they use this information. As I went back, as I want to go back to my earlier slide, all this is a tool to start discussions. And the fact that you even brought that up is, proving to me that this is probably a discussion that some folks at some watersheds are going to have of what these constraints are and what they actually mean. I mean, they didn't even have this information before, but now they have the tools to begin asking questions like that. But I agree, it's a very tricky one.
About the reference site, just was wondering kind of how you account for the variability in the density of reference sites in particular areas of the state, and then so for example, more urban areas like our all of the reference conditions or some of the particular regions, and then kind of how you account for the potential degradation of reference sites amongst.
Right. So the question was about reference sites, and does the model account for variation among the state in areas that might not have adequate representation of sites? So there's an easy way to answer that. Going back to the CSCI, that is something that was developed statewide, and there was a whole process going into the development of reference sites for, not specifically for the CSCI, but just in general, what are the reference sites? So from the technical side of the bioassessment index, that is something that has largely been taken care of. But the second answer is, I think what you asked me was the reason why we developed this tool. So the South Coast region, heavily impacted by urbanization. In a lot of places where we have scores, there are no reference sites. So if you think about it, this model is a way to sort of look at that in a little more detail. It's like kind of like a reference relative to a reference site. The argument is LA streams in urban environments are never going to reach reference conditions. So how do we define a reference relative to that? And that's kind of what we're trying to do, sort of account for different contexts relative to a larger context that might be defined by the reference condition. So it kind of implicitly gets at that. Does that answer your question?
Yeah.
Okay.
So I'm trying to think how to make your question and figure this out in a little way. So one is that the water in the U.S., water in the state, and one is but the other is a little easier. That it seems like the red zone. In fact, in my mind, I think a red zone is a place to go to act.
Yeah.
But it seems like it's possible that they could just fall into this red bucket that and you just don't do anything about it anymore. We kind of forget about it, and it contributes to that shifting baseline, like
yeah.
they're worse, we accept that they're worse, and so we just leave them because they're worse. And so having that red bucket on one side, saying those are low priority, kind of reinforces that.
Yeah, no, that's the biggest issue people have with this approach. But I just want to emphasize it's not what we're trying to do. We're not trying to lower the baseline. I mean, you could make that argument that this is kind of one approach to do this, but on the flip side of it, if you're in a situation where you have, in the case of the San Diego watershed, 200 sites you have to manage, being able to prioritize among those and doing something at some of the sites is better than nothing at the sites where you just sort of wave your hands. I mean, even in that lower watershed, there were instances that we identified where there could be meaningful action. They didn't have that information before. And prior to this model, they were probably like, well, we have no idea what to expect here. And so we're able to give them that power. So just to reiterate, this is a discussion tool. It's not the be-all, end-all. The other point related to that is, this is a tool only in the context of the CSCI, so only in the context of macroinvertebrate assessment. Just just because we're defining constraints relative to the CSCI doesn't mean it's relevant for, say, algal assessment or even physical habitat. There's other pieces at play here. This is just one facet of the larger needs of, I guess, assessment and management in general. So there's other, I mean, yeah, at the risk of adding more things on the pile of how to, what to consider when you manage, I mean, we're kind of doing that in a way, but we're doing it in a way that is particularly relevant to the CSCI. But there's other evidence to think of. Yeah, it's a very good point. I mean, because I totally agree. So the issue you were mentioning was, on the other side, you have these sites that are other less developed parts of the state that are doing quite well. The folks that are managing those systems don't necessarily want stricter regulations. If we're going to say they're doing well, let's protect them more. Again, it goes to me that goes back to working with the local stakeholders and defining what the priorities are. The hardest part of this project was getting the stakeholders to agree on the meaning of those priorities and what, how many different bins of those priorities. Because we had regulated folks, regulators, monitoring groups, nonprofits, you name it. So we tried to get a whole diverse group of people in the room to sort of discuss their needs. And if people are managing resources for different reasons, that the needs are clearly different. So to sort of the short version to your answer is if you're going to talk about these unconstrained sites in other parts of the state, protect might not be a good category. So if I had the resources to reward, I certainly would. But this is about using limited resources. But your point is well taken. Yeah, so you're talking about the model development and the variables that went into it. It was a mix of, so we had two separate versions of the model, a full model and a core model. The full one was everything in the kitchen sink related to land use development. We didn't go with that one because it's kind of a lot. The core model was a select set of variables, and if I remember correctly, it was a mix of, I think, catchment level and watershed level metrics. So it's how it's defined within the StreamCat database. Yes, it's the NHD reach. Yeah. Yeah, and actually, it's sort of an anecdote here. There are some sites that we noticed that were overscoring in these urban environments, and if you actually, the app we developed lets you pull up the satellite layer, and you can actually look. And I did notice that some of these high-scoring sites, and yeah, they're just in these green spaces. I'm like, yes, the model's working. So at least at that level that we've defined it. So. Okay, thank you. Thanks.
To round out our bioassessment section, and before our lunch break, I'm going to introduce Calvin Yang from the Office of Information Management Analysis.
Okay, thanks. All right, thanks everyone for sticking around. I know it's lunchtime, so I'm going to be presenting in a more general sense of how to use an interactive dashboard to communicate bioassessment data. But before I start, I just wanted to mention that all the partners displayed here on this slide have helped build SWAMP's large bioassessment data set. The data and tools would not be possible without them. So why create a dashboard? Well, SWAMP's mission is to provide resource managers, decision makers, and the public with timely, high-quality information to evaluate the condition of all waters throughout California. So SWAMP has multiple monitoring programs and and Florence bioassessment program evaluates the physical, chemical, and biological integrity of the state's waters. And here are a few pictures of the benthic macroinvertebrates that are sampled. So, in order to evaluate the biological integrity of the state's waters, SWAMP uses two statewide monitoring programs to provide context for assessment. The Perennial Streams Assessment, or PSA, collects ambient data by using a statistical survey to answer the question of what is the biological condition of all California streams and what is the condition of streams that drain agricultural, urban, and forested land uses. The other statewide monitoring program is the Reference Condition Management Program, or the RCMP, and that collects reference data using a targeted sampling design to answer what is the biological expectation of healthy streams when human disturbance is absent or minimal. And some of the things that are, some of the criteria that's used to define references, things like number of road crossings, you observe bridges or trees cut down or pavement at the site. And so the PSA and RCMP both collect benthic macroinvertebrates, benthic algae, habitat surveys, and water quality data. And both of the data, the data from both statewide programs are available to download from the California Environmental Data Exchange Network, or CEDN, and also the California Open Data Portal. And I just have on the slide just a few example data sets of what you can expect to see. And so just a picture here I just wanted to mention is, so this is a picture of a Leucochaeta, which is found in all types of waters, including highly polluted areas. As far as habitat data, we have data for canopy cover, which is measured using this densitometer. And then the types of water quality data that we do collect is also displayed here, so it's things like conductivity and nutrients. So after you've downloaded all this data, how do you make sense of it? How do you incorporate the information about how Leucochaeta is found in all types of waters? Luckily, that's already done with the California Stream Condition Index, or CSCI, but what happens if you have multiple CSCI scores? What if you wanted to know where are the healthy biological streams? What is the ambient biological condition in the North Coast region versus the San Diego region? So that's where a dashboard comes in. A dashboard allows the user to organize and analyze data so it can be turned into information. Instead of spreadsheets of raw data, like looking at just this, the user can communicate their findings to colleagues and management through maps, graphs, and summary tables. Another way to define a dashboard is that it's also an interactive report, which means that it can map, graph, specific data set or a group of data sets based on what the user is interested in. So say you have the question of where are all the intact or where are the intact or healthy biological streams? So what you could do is then on this dashboard you can click on the drop-down menu under the CSCI condition, click on likely intact, and then the map will just display only sites that are within, have CSCI scores within this condition. The summary table here on the right has parameters that were collected at those sites, and then has basic statistics that go with the results. So how many of those samples were collected for those parameters, the minimum value, the median value, the average, and the maximum. So everything's all in one place for you to look at in one visual. And then the other visual that's also in this dashboard is a bar graph, which displays all the different land uses in one area. So it's breaking down the same data, but by land use. And the land use luckily was defined nicely by Bryn in his talk, which was using the National Land Cover Database. And then just something I just wanted to point out as far as answering this question of where are the healthy biological streams, the bar graph shows that 184 samples were taken from the forested land use that fit this condition, whereas in contrast, only 10 samples from the urban land use and 4 samples from the agricultural land use fit this condition. If you had the question of where are the altered or unhealthy biological streams, you could use the same drop-down menu and then click on the very likely altered, and then the map will just display sites that fit that condition. And the summary table and the bar graph will then update as well. Something I did want to point out in the summary table is that you'll notice that chlorophyll A and conductivity, the median results for those parameters are elevated, and which means that the majority of the streams have this results. And the reason why I want to point those two out is that chlorophyll A is a predominant type of chlorophyll found in green plants and algae. One of the symptoms of degraded water quality is the increase of algae biomass. So that's, along with your CSCI score, adding water quality parameters data to evaluate the stream. And then conductivity, as you all know, is a measure of the ability of water to pass an electrical current. Increases in conductivity may indicate that a discharge or some other source of disturbance has decreased the health of the water body and its associated biota. And then just to look at the bar graphs again, you'll notice that only 14 samples from forested land uses fit this CSCI condition, whereas over 200 samples from the urban land use and 40 samples from the agricultural land use fit this CSCI condition. If you wanted to just look at data from just the San Diego region, you can click on the smaller map for San Diego, and the map will display only sites that fit within that region. And then the summary table and the bar graph will then, again, just display results from those sites. And as far as answering the question of what is the biological condition in San Diego, so just based on the probabilistic sites that were within this region, the median CSCI score is 0.78, which fits into the likely altered CSCI condition. If you wanted to look at just North Coast region sites, you would then also click on the North Coast region, and then the map, the summary table, and the bar graph will all update as well. And then the median CSCI score for this region is 0.92, which is in the likely intact condition. If you wanted to look at the Lahontan region, you would also just click on the region on the map, and then the map, summary table, and bar graph will all update as you click on that map. And the median CSCI score is also one which is in the likely intact condition. So the point I'm making by going through all these examples is just to show you that the dashboard gives you instant feedback. It can map, graph, and summarize different data sets. You can filter for just intact or altered biology. You can filter for regional border specific data. And the bar graph displays results by land use. So everything's in one concise view for you to look at. If you had another question about what is the biological condition of urban or of streams that drain urban land uses, you can click on the slider here and just move it to urban land use, and then the map and summary table will update as you select it. And these are just zoomed in pictures. The map you can zoom in and just look at just where the sites are displayed on the map. And then if you want to look at just agricultural land uses, you would just use the same slider and the summary table and the bar graph will update as you select it. And just want to make sure I answer these questions. So the question is of what is the biological condition of the streams that drain these land uses? And you'll notice that the median CCI scores in the summary table is 0.56, which is most streams in these land uses have altered biology. So just with these examples, I just want to show that for the streams that drain these land uses, they do have altered biology based on the CCI scores. Most urban streams do have high chlorophyll A results, which is a symptom of degraded water quality. And both land uses also have many streams that have high W1 Hall results, which is an acronym for Riparian Human Disturbance Index, which is used to interpret physical habitat field data. And then hopefully this is a follow-up to the question that was answered, or that was asked in the last talk. So where are all the reference streams? What you could do then is then just click on the checkbox just for reference, and then the map will display only reference sites statewide. And then the summary table and the bar graph will update too. And the median CSCI score for all the reference streams is 1, which is in the likely intact condition. And also, if you just wanted to look at reference conditions within just a certain region, in this example, I just selected region 5, and then the map, summary table, and the bar graph will just display results and sites that fit within that region. And from the summary table, the median CSCI score is 1, so that's also in a likely intact condition. So, I'm making good time. But so in summary, I just wanted to, I hope that you guys take these 3 points from my presentation. Dashboards can help management make data-driven decisions because they're using maps, graphs, and summary tables instead of spreadsheets of raw data. And then users that want to interact with the data, the maps, and the sliders and checkboxes, they can do all of this through a website. So there is no extra software you have to download and install. People can just go to the link and then interact with the dashboard from there. And you can also download the data once you're done with the dashboard. And then the third point is just that the dashboard can help communicate monitoring results at the regional and state level. And even at both levels, the urban agricultural land uses tend to have degraded biology as measured by the CSCI. If you are interested in more about just interacting with the dashboard yourself, you can click on this link here or just search Tableau Public, and then this link should pop up first. And then once you get through that link, you can just search again for Communicate Bioassessment, and this dashboard should be the first thing that pops up. And if you want to learn more about Swamp's bioassessment program, you can also click on this link or just search Swamp Bioassessment, and actually this link will be the first result that pops up. And thanks for listening, and have a good lunch. Sure. Oh, shit.
Great presentation. I had a big question about the other land use category. Did you mention what that includes?
I did not. That was a good catch. So it's similar to what Brendan was talking in his talk. So there's certain percentages for agriculture, for urban, and for forested land uses. The other is when the land use actually doesn't fit within those criteria. So if it's less than 25%, less than 50%, less than 75%, there's actually a lot of sites that do fall in that, so that was the other category.
So those are public and private land?
It should be both, yes. And so these data set that I went over is the statewide data set for PSA and RCMP. Okay, So the question is there a plan to add benchmarks to the dashboard, to the visualization? That wasn't in the plans, but it's a good feedback to hear on the dashboard. One of the things that's nice about creating dashboards is that it's easily customizable, so I could just go back to the office and then just add different data sets or add things like that, benchmarks, to the visualization. So if that would help put the data in context, then yes, that could be done. Thank you for that feedback. So the question is, are we, in the dashboard, could you add sample reaches instead of just dots on the map? And that wasn't in the plans too, but it is something that we did initially. So this dashboard is actually maybe version 6 or 7. So that was initially in the map, and then it was taken out just because one of the things that we were going through the visualizations is, so you create the visual and then you give it to the users. Does it make sense? Do they understand like what they're looking at? So that is something that I could explore again. Thank you.
One example of a dashboard that can be put together using the open data, and which is really the power of having the data open and accessible to anybody. You can tailor these kind of products using Tableau or ArcGIS and other kind of tools to answer the questions that you're specifically looking for. So you can add these layers in depending on what you're wanting to ask, what parameters or what objectives you're interested in. This is just one example, a great example of, he was asking what is the CSCI in my region, what's the CSCI as a factor of land use. We can add in and tweak those knobs based on what you want, but the whole key is to have that data available for you guys to innovate and use to answer your specific questions, and then make that information available and then communicate it in a specific way. Welcome back, everyone. I hope you had a great lunch. We're going to kick off our afternoon session here with a great talk by Greg Schumer from the Genadax Lab at the Kramer Fish Sciences. He's going to tell us all about eDNA.
Thank you. All about eDNA, nothing like molecular biology after lunch. So if anybody gets sick, let me know, raise your hand, I'll stop talking about DNA. So we're going to go over the basics of eDNA and then some applications of eDNA for a few species that we've been working on for the past few years, and then I'll go over communication of the data itself. The data itself is not always easy to deal with or visualize in context, so I'll go over a little bit of what we've been working on for that as well. And then how do you collect it? Like, what kind of tools you need, what are you going to do with it? When you get a sample, how you process these things. Excuse me. So what is eDNA? eDNA is just biological material floating around in the environment. For this talk, we'll talk exclusively about aquatic eDNA. So it could be anything from fish guts, poop, urine, cells, eyeballs, whole tissues, hair, whatever it is. As long as it's from this planet and it came from an animal that's alive or dead, it will have eDNA in it. It'll have DNA in it. It's a DNA-based planet. So if you're in the water and you can filter that water, you can find DNA out of it. You want to find specifically the target species you're looking for, of course. I'm not going to go into the details of the black box lab stuff, but maybe we can cover that in the Q&A session. But just for today, we're going to talk about sampling and applications. eDNA is a particle, not unlike other particles. It does have its own unique properties, and the math of that is being worked out right now by a lot of people, including the Defense Department. It will behave like a particle in the environment. The more source material you have, the more individuals you have giving up their cells and their tissues to the environment, the more DNA you will have floating around in that environment. If you have an individual, you can reliably detect an individual fish to about 200 meters, given a few circumstances. You can filter enough water and you can actually get to the site. The more images you have, naturally, the more stuff you have floating around the environment, the easier it is to detect that. The higher the probability is that you can actually detect these particles from within the environment. So as long as you can still sample that environment and filter that water, you will be able to find the cells, the tissues, and the DNA that lies within. If you have a stagnant environment, you just have to shift your sampling technique a little bit. So if you're looking for anything inside of an environment that stratifies, the DNA will fall out like a normal particle, and it will go to the bottom, and you may have to sample a little bit differently. You will have to sample differently. So for today, as I mentioned, we're just going to discuss aquatic eDNA. This eDNA has been, the field of eDNA has been around for quite a while for farmers. So if any of you are soil people have been sampling bacteria in the soil for 20, 30 years. If you're an air person like this building, they've been sampling filters to make sure there's no diseases and being pumped through the air system for 10, 15 years as well. So eDNA is not a new concept. Its application to the aquatic ecosystem and ecology and monitoring of the ecosystem, the aquatic ecosystem, is a new thing for ecologists, aquatic ecologists. But the techniques, sampling the environment, filtering water, extracting DNA, and analyzing DNA, these are all tried and true practices that have been in the literature for 20, 30 years. How you analyze it won the Nobel Prize in '94. So we don't really need to work on that kind of stuff. It's just how do you sample the state of California? How do you do that? So the way we go about as geneticists and molecular biologists and ecologists at genetics, we view our job as doing three things, which where are the organisms that are protected, state federally listed? When you figure out where they're at, which is not always easy for any of you that study delta smell, figuring out where they are exactly is not an easy task. Once you do figure out where these things are at, and you need to figure out how many are there, what's the size of the population, and how is that population doing? Are they big? Are they diverse? Are they multiplying? Are there kids multiplying? So success for us in genetics and molecular biology is your grandkids. But eDNA is strictly about where are they? Where are these organisms in the environment? That's all we focus on with eDNA. Once you figure that out, then you can go on to the next two steps, which is how are they doing and how many are there? So far, eventually the technology will get to where we may be able to do other things with eDNA, but right now it's just, are they here? When does it make sense to use this technique? Can you find them any other way? If you need a net, if you're looking for striped bass, you don't need eDNA. If you're looking for a common species, you really don't need eDNA. But if you cannot find them, like giant garter snakes, or you can't trap them using modern techniques, trapping techniques, or if a slew of boats can't find your species, you can't get a permit. Nobody will issue a permit because it is a protected species. eDNA does not require, aquatic eDNA does not require a permit at this point. And what are the goals of your survey? Do you want to know the population size, or do you just want to know occupancy? Are they here at this time, in this place? Then this eDNA is a good tool. So how do we go about doing this? There's a couple of techniques out there. There's a couple different filtration techniques. We've developed our own based on my background in human pathogens, because I'm ultra paranoid about contamination, cross-contamination of samples. So I've developed a method, and we published it using some really basic stuff. And this is common between everybody. Anybody who's doing eDNA out there needs to pump the water through some sort of filtration apparatus. We use a screw and that pump, and I bought many, many pumps, fancy pumps, self-contained pumps, waterproof pumps, battery pack pumps, rechargeable pumps. I took every single one of them apart. This is about $250, and that's $100. So for about $350, you can have a sampling apparatus. Then you just need tubing, silicone tubing, end caps. This is a Sterivex filter. This is the difference between what we do and what basically the U.S. Forest Service, U.S. Geologic Survey, pretty much everybody else uses a flat disc filter that sits on top of the filter funnel. And when you're done filtering, you have to remove the funnel, twist the filter, shove that filter into a tube, Send that tube back to the lab, you take that filter out, you cut it in half, you extract both pieces. So there's a lot of opportunity for contamination, which freaked me out in the beginning. This is a EPA-approved Stervex filter. It's self-contained. It comes with end caps. So when you're done pumping your water through this thing, you just shove end caps on it, label it, and there's never a need to take that filter out. I can extract DNA right off that. So I can liquefy organics inside of that thing right there. So contamination is really hard. I've tried to contaminate that. It's very difficult. And it's pretty basic. You stick one end of your tube in the water, and you push it through the filter. It's a unidirectional filter, so you can't screw that up either. And I've tried to screw that up too. If you put it on backwards, it just keeps flowing and flowing and flowing. It was like, wow, we're getting a lot of volume out of that, but actually it's not doing anything at all. And like I said, at the end, you just pull it out, and you can measure your volume, because that's important. You got to figure out how much of the environment you're measuring. And in the end, you just cap this thing off and label it. I stick that in a Ziploc baggie, and I put you can extract DNA within a week or more, but I try to do it within a week, and you get to the DNA stage, it's extremely stable. So the other things that we think about when you're sampling any aquatic environment is how do you do this? How many filters do you need? How much volume do you need? Where do you need to be? How often do you need to get there? There's quite a few questions. So we worked out these variables that we try to determine for any new species that we are attempting to detect by environmental DNA. There's the volume of the environment that you can filter. There's the pore size of the actual filter. The larger the pore size, in theory, the more water you can get through it, which increases your volume. So you need to worry about the filter itself. How far away from the source of the eDNA can you be and still detect it reliably? And how much of this can you detect? Is it one fish? Is it 1,000 fish? How many, what's the context of this? And the number of filters required to do all of this. How many? Do you need to take 10 filters, or do you need to take 3 filters? What are the bounds that you need to stay within in order to reliably detect your target organism given your environment? These are typically what we work out in every scenario with every organism. And once we figure this out, then we can go out and start to say things about how far away we can get from a given number of organisms and filter this much volume in this place to detect this species. This is the problem. This is coming out, it should come out any day now. This is from the EPA, who we've been working with in the Central Valley to look at delta smelt occupancy throughout the delta and some vernal pool stuff as well. They went through and did some modeling on how many filters you need to take to keep your probability of detection up around 100% given the size of your watershed. What they found is that within about a 50 square kilometer watershed, and this is a low volume, like a 500 ml and a 1 liter sample. If you can take up to 10 samples, 10 1 liter samples, given your filter size, in a 50 square kilometer area, you still have a probability of detection that's 1. It's pretty good. So we tend to stick over here. We're over in 3. Our watersheds are typically small. We're getting into larger watersheds now, so we're increasing our filter size. So our area now is the delta. Really small unidirectional creeks looking for a frog or a trout. This is fairly simple, but when you increase that scale to the size of the estuary, now you've got some. It's very difficult to find a delta smelt in the estuary. So how do you go about doing this? Well, you calculate a probability of detection. What's the probability that you can detect a delta smelt in a unidirectional system? And this is the CVP, the Central Valley Project, for those of you. This is the canal that goes past the Central Valley Project, and this goes up to the pumps and then into the aqueduct. Just so happens that they salvage fish right here all day, every day, 365 days a year. So we decided to calculate a probability of detecting a given species, in this case it's delta smelt, given distances away from the source, a known source. So we put a known number of fish in the water, and then we worked our way away, started from down here, kilometer away, and we worked our way back up towards the source, taking filters all the way, taking a given volume all the way, and then we extract the DNA and you analyze it, and this is how we calculated a probability of detection delta amount. So it turns out at the facility, given the conditions that we had, our filtration setup, our ability to extract DNA, given everything that is unique to us in the lab, our probability of detecting delta amount 40 delta amount was as low as we could go. We could have gone to 1, but we didn't. We wanted to get some data, and we're still working on the model that goes with this. With one filter, the probability of detection was 100 fish. 100 fish with one filter at a distance of 200 meters with our filter at a 300 ml sample, which is not a lot considering the size of the environment that we're sampling here, was 60%. So probability of detection is 60%. So if you just do the math on this, and this is standard sampling math. If you double the filters, you go up to 84%. 3 filters is 94%. 5 filters is 99%. So you can just keep taking more and more filters and extracting DNA off them. Garter snake DNA. I'm not an ecologist either, you guys. So a lot of this stuff is really new to me. So it turns out garter snakes, giant garter snakes, apparently are really hard to find. Eric Hansen, that's his whole life. His dad did this, he does this, he's the garter snake guy. That's what I call him. He's the snake guy. If anybody can find garter snakes, it's this guy. He came to us because he couldn't find garter snakes anymore, given trapping and a kayak and all that. He was putting out 2,000 traps a year all over the Central Valley trying to find garter snakes. Couldn't find them. And in the process, he was missing his kid's life. So he came to us and said, look, I can't see my kid like 6 months out of the year because I'm busy driving around the Central Valley, putting traps all over the place and not finding snakes. So could you help me find snakes, please? And of course, not being an ecologist, I said, of course, how hard can it be? It's just DNA in the environment. So he went to this is a known source. This is the Volta Wildlife Area. So there's documented evidence of garter snake occupation here. This is a unidirectional flow. There has not been documented garter snake in this canal in over 11 years, 11 to 13 years. So we did the same thing. We just wanted to go do this. How far away can we get from the known source, which we don't know the number, so it's hard to work out the probability of detection. How far away could we get from these garter snakes and still detect them? So it turns out we get about 300 meters away, given the flow, which is very minimal, and I don't have any pictures of this water, but it's bright green, and it was hard to get more than 100 mLs through a filter. So with 2 filters, we were detecting garter snakes at 300 meters away, which is pretty good. And unbeknownst to me, he went through and took a bunch of other samples, and we were just working by mail at this point. He was mailing things to me, or he'd stop by the lab and give me a bunch of filters. He coupled his eDNA observations with a bunch of scent dogs. Apparently there's scent dogs out there that can smell garter snakes in the environment, and they take these things around and they smell garter snakes. So he was coupling these things. He was out there with the dogs, finding snakes smell with the dogs, and then he would take an eDNA sample, and then he'd mail me and not tell me at all. Until I went to the garter snake convention and gave this presentation. I was like, oh, hey, these line up really well. So these are where he traps, and he had no documented trappings, none. He went to this site, so he went here, let's see, I can't remember. Anyway, he went here and he took the dogs there, and one of the dogs jumped off the kayak, apparently, because he keeps them on the end of his kayak. Jumped off the kayak and went to shore, and he laid a couple traps where this dog jumped off. Sure enough, he got a snake. He took a bunch of eDNA samples, and I found the DNA in the water as well. So we had a triple observation of a documented garter snake, giant garter snake, at a site that had not had a documented garter snake in many, many years. And I didn't figure this out until later, because nobody tells me where they're taking these samples, which I kind of like. I kind of like having these blind things. Then I get shocked when so here's another blind study where this guy, he really likes frogs. And tiger salamanders, I mean, he's out there looking for all kinds of stuff, right? So this is the same thing. They came and said, look, we have these mitigation banks, and you know, some of these landowners are considering just selling them, like getting rid of them, because you can't document the species that they're restoring these habitats, these land. They're restoring this land. They're spending all this money. They're holding off on development. They're doing all these great things, but then nobody can find the actual organisms that they're trying to save. Nobody can document them. And in this particular case, the landowner was at his wit's end. He's like 30 minutes outside of San Jose on this piece of property. It's probably going to be way more beneficial for him financially to sell the hundreds and hundreds of acres he had in the foothills outside of San Jose than it would be for him to keep cow ponds available to animals that nobody can find. So again, they came to me and said, okay, can we filter this? Can we go to this property and filter all these cow ponds? And it was literally nasty cow ponds. I threw away my boots after I was done with this because I didn't think there was any way to get this funk out of them. And typically what they do is they walk through, they drag this net, and if nothing's there, well then nothing's there, right? There's no critter. But we went through and we filtered all these sites, literally these streams running through fields, these big ponds, and what we find, this is, I'm not gonna go too much into this, but for me, this is what a positive looks like for me. This is a control. Yeah, can I do what I say I'm doing? Yes, this is a control, that's a control. And this is what DNA looks like when it amplifies on a graph. So I said, oh, you know, go back and check these ponds because I'm finding the DNA in these ponds. Sure enough, he went back. Not only did he find the tiger salamander, and I don't know which one's which, PETAs, but he also found the red-legged frog. So he found 2 endangered species in these ponds. So he went back to the landowner, and, you know, I'm sure they all high-fived each other, and it was probably like, I picture them like landing something on Mars. Where they're like, yeah, I'm going to be rich, or I don't know what they're doing. Okay, so translating. So we've tried to translate this in a lot of ways, the presence of DNA in the environment, and tried to communicate it to people. It's very difficult. What we came up with is this funky red-green system, which is, I hated it. And I always picture the guy in Close Encounters of the Third Kind, like trying to communicate with aliens, where he's like, look, just listen to us. This is what it means. But really, that does not work for me because I can't picture it. So what we've been working on is a Shiny app where we graph out the occupancy data, and then we just get in our studio. Oh, it's shut down. We gotta reload it. So we just take the data and we put it onto a web interface so that we can actually play around with it. We can turn things on, turn things off, and see what DNA is there and when, at which site. Now we gotta wait for it to load. Because it's really hard unless you put these things on a map. Because you're looking for the presence of the indirect observation of an organism through the presence of DNA in space and time. It's not easy to communicate, really. You need to be able to visualize the data. I need to be able to visualize the data. Like I said, I'm not an ecologist, so for me it's very hard to figure out where things are coming and going. And this isn't the end. This is just where we're at. So I don't want anybody to think that we took hard to communicate data and just made it really ugly and harder to communicate. We're working on it. Okay, so these are different sites and these are different species. So when you start to eliminate things, you start to look at these things in space and time, you can actually start to see, this is fish salvage, these are species, and you can just add more species and you can just place these things on a map essentially. And what I would hope to do is just take the map of the delta and just have live data actually flowing as the water would flow. So as these organisms come and they go around the Central Valley, you should be able to see the presence of the DNA come and go, just like the species do themselves. It's not an easy task. It's the one I've given myself since I started this about 8 years ago, because in my mind, if it's a system, it's an ecosystem, it should function like a system. You should be able to look at it like you look at any other system, like a human body, right? You should be able to watch things come and go, like cholesterol or a disease. It should work. You should be able to see smelt in the delta come and go. You should be able to see salmon. You should be able to see the life that inhabits the environment come and go. And that's it. I'm right on time. So we could do both typically, because it's a good question. The question is, can we look at more than one species from one sample? And the answer is yes, you can, which is a great thing about this, because you're extracting all of the organics out of the environment. You're not just getting the DNA of the thing that you're looking for. You're taking this filter, extracting all the DNA out of it. Then you can go back and look for any DNA. You can look for bacteria or viruses or delta smelt or salmon or deer or humans or whatever you want, because it's all theoretically inside of that sample. If the species was there, their signature should be there. So we have a list of species that we look for, the common delta species, aquatic species, or the ESA listed or endangered species. But you could also metabarcode, which is where you enrich for a specific target that just gives you kind of a community-wide evaluation. You say, what's there? What is everything that's there, and can we detect it and just make a pie chart of all of the organisms that could potentially be there? So there's a couple ways to do it. But yes, you can look for any number of species. You're limited by the amount of DNA that you have. At one point, you could just reanalyze until you run out of DNA. Yes.
What's the lifetime of the DNA?
It's contemporary. If it's in the water column, it's contemporary. It's hours to days. If you go into the soil, this is something different. Like, farmers have been doing this for a long time. They've been detecting DNA out of the soil for a long time. If you go into the soil, if you dig a core down, you're going to find DNA that is not contemporary.
And how much effort is required to take something like that?
That's a very good question, one that we're trying to answer, and I'm consulting an economist almost to see how to go about doing this. But we charge $150 per sample. And we bought a boat, and we bought a bunch of pumps, and we have a bunch of employees. So now we're driving around the Delta trying to take samples, but it's really hard. So we're trying to coordinate with programs within the IEP, programs that are already in existence that have $1 million boats and 5 people on them, and there's 10 boats out there. The Delta is intensively studied. At any one time, there's probably 20 people out there looking at something somewhere in the Delta, and it takes 5 minutes to bend over and take a filter. It's not that hard, right? So, the money is already being spent out in the field to get all these, because the money's in the field. The money's in getting the people and the stuff to the field. It's not in a screw gun and a parasolic pump and a $7 filter. Like, if people mail me filters, or whoever, the university filters, this isn't a sales pitch, really. If people could just coordinate the DNA extraction over time and space, that's hard. But that's, to me, what the IEP does already. They coordinate multiple sampling activities across 5 or 6 agencies, and they're spending huge sums of money on it. So I think it could enhance that activity.
Have you seen this sampling method being put in place as far as maybe
we are using it, but I don't deal with that side of it. So a few of my clients use it at their mitigation sites, yes, and it has been requested by whoever oversees that mitigation bank, Fish and Wildlife or Cal Fish and Wildlife, or it's being requested now in FERC relicensing. So we have a couple projects for relicensing projects. It was requested on the Bear River. It's down south. This past year has been an explosion of use. We're having a hard time keeping up. The regulatory agencies are starting to use it, but it depends on who at that agency you talk with, right? It's siloed right now. But yes, we do have cases where it's being used on mitigation banks. I don't know them. There's one in Gilroy. I try to stay away from that side of it, really. Yeah, I do, because I really don't know anything about it. So I like to keep it that way. I don't want to disagree with things that are going on, or even agree. I just want to look at, like that graph, like the graph, right? Like, I'm okay with that graph. When I see something pop up, DNA pop up on the graph, I just report it to the client and say, there is DNA at this place from from this filter. You can provide the context external to that. Yes. Hey.
How's the data structured, and are there any recommendations that you have about this data become more integrated with other kinds of DNA data or any other kind of waterborne data?
The DNA data, it's from what I've seen in the literature, is that it varies lab to lab almost who is doing the analysis. So, which is why I always recommend duplicity. Just take more samples. That's why we take a lot of samples. So it's hard to standardize this right now because everybody is out there kind of using their own field technique and then their own lab technique and then their own reporting standards. So we've been trying really hard to standardize some of it. Now, standardization can be bad as well because it kind of eliminates imagination occasionally and could be a bad thing. So I find it, but there's certain things you can do to adhere to standards. And for the lab, there's something called the MIKE guidelines, which is a set of guidelines established by the analytical chemistry community 20 years ago, and there's books written on it. But anybody that publishes data, quantitative PCR data, which is how you report this stuff, you have to adhere to these guidelines. And if you don't, you can't publish it. So I think that's a natural place for the laboratory to go. Now, the field, we try to stick with the ASTM EPA recommended standards for sampling the aquatic environment, which is not easy because we're doing DNA. This isn't fecal coliform at a water treatment facility, right? So we're trying that out, and we're trying to calculate the probability of detection and how many filters you need. And gosh, if there were an eDNA filter in existence, if some filter company would come along and revolutionize the filter field so we'd all have a standard or a standard set of filters that we knew we would all have to use given the situation, that would be helpful. I'm trying that angle as well. I'm trying to convince large corporations that make filters to make better filters for us specifically, but that's hard, right? They want $50,000 just to change their manufacturing process. So that's a limitation for people, $50,000 is a lot of money to us. But those are a few things. Filtration, what's that? Well, yeah. Water in California, 50 grand is we just spent that. We just spent that on the insurance for this meeting, probably. Anybody on the phone have a question?
No, they can't.
Oh, they can't?
No, they're just listening.
Oh, okay. Anybody else? I got lots more answers. Well, that's, I like this guy. We're going to go get a beer afterwards. Did you guys see the article for the Loch Ness Monster? They're doing eDNA for the Loch Ness Monster right now. We're not doing that, but I thought, geez, with all the Bigfoot people we have in California, we're taking all these samples. Why not? See if we can find some strange DNA in the environment. So I'm going to try to get a sample from one of these Sasquatch museums to see if it actually I'm going to try to just extract DNA from a hair sample that could be Yeti. To stay next year, you guys, that could be the... So I'm trying to find the strangest thing in the strangest places. But so far, we just find what we're looking for, which apparently is quite strange. But a lot of these ecologists I've met, they're like, wow, I have never found that animal here before, and thank you. So it's helpful. Thank you.
Thank you. So next is our management panel, which is going to be moderated by Craig Gearhart, who's the Deputy Director of the Office of Information Management and Analysis. Our panelists could please come up. Up first is Dr. Christopher Dillis from the North Coast Water Board, followed by James Smith, the Assistant Executive Officer of the San Diego Water Board, Dr. Stephen Weisberg from Southern California Coastal Water Research Project, and Jonathan Bishop, the Chief Deputy Director of the State Water Resource Control Board.
So hello from way over here on the other side of the stage. Thank you guys for coming and joining us in this panel discussion today. We're going to run this panel in a pretty typical format. This is meant to do a couple things.
kind of bring it home. We've been having a lot of great discussions over the last 2 days about particulars of water quality monitoring, water quality science, data visualization, management questions that are driving some of this stuff. This is meant to be a bit of a wrap it all together and have a dialogue, and the consumers of some of this stuff would be represented by our panel. So management people, or people running management questions in their heads or they're in their programs, and how are they going to make use of all this great stuff that we've heard for the last couple of days. So thank you again for coming to the panel. The format is going to be each panelist is going to get about 7 minutes to give a presentation about their relationship with data and where they think data-driven approaches could be improved from their perspective, and then I'll moderate some questions throughout the panel. So I think first up we have Steve Weisberg, and he has some slides. I want Steve to go first.
Okay.
All right. So thank you, Greg. Hopefully you all can hear me in the back. Okay, good. I want to start with the biggest driver being climate change. And on this graphic, I want to get across what I think are 2 main ideas. The first is, as you look across the top, you'll see that I think there are 4 main drivers within the water quality data need arena. It starts with atmospheric CO2, but it quickly goes to direct CO2 going into the water column. And so that's one of the drivers, is that you're getting a change in acidification in the water. The next 3 are ones that are a little bit more indirect, where you have CO2 leading to climate change, which in turn then affects things like sea level, hydrography, changes in flow, and changes in temperature. So those are the 4 things I want you to be thinking about, because I think those are the things that, you asked me, Greg, to talk a little bit about how the changing landscape with respect to climate change. Those are the 4 drivers. But I also want you to look down the side, and what you'll see is 4 things there. It's basically the stressors that lead into impacts that lead into management action. And so the challenge, I think, for the group that's assembled today is how do you connect those? And I would suggest to you that if you look at the piece on the top, that's where most of the scientists who do climate change are working. They're really quantifying how important the stresses are, how quickly those stresses are happening, and even some of the things that are leading to those stresses. In other words, where is the CO2 coming from? But most of the things that the people in this room have to deal with are at the bottom. And it's the things that are management, either the parts that's the impact, that's where we go and do the monitoring to quantify the effects, or where we have to do the mitigation actions and assess the effectiveness of those. And so I think what I'd like to do in my, you told me 10 minutes, I'll try and do 8, is kind of connect those 2 and talk about what that connection is and what some of the things are that drive different data needs. I'll start with the one that's closest to my heart, which is ocean acidification. It's closest to my heart in part because it's what I'm spending a lot of time working on, but I also think it's so important because I think of it as the thing that's going to drive, it's going to be the defining issue for my generation and probably some of the ones that follow from it. The starting point for me is we know from monitoring that the ocean is acidified. We also know that the biology is being affected. So we know, for instance, that things like pteropods, the shelled organisms, have pitting in their shells. We know it has even gotten to the point that the oyster hatcheries having difficulties, and they have to be managed differently when they take their water intakes. In fact, the best monitored acidification tools in the country are at the West Coast shellfish because they're actually using it for making decisions. But for us, we're only beginning to think about this from a science and from a management perspective. And it really starts with, we don't even have acidification targets. We don't have acidification criteria. We don't, I talk about the biology, we are measuring the biology. We know that the shelled organisms have pitted shells, but is that really what we're worried about, or do we only worry about it when it gets to the point that the organisms are having kind of a fitness change, so their reproduction or their growth is affected? We haven't even begun to define what our goals are, and you can't manage unless you have goals. Or you can't do the monitoring unless you have the goals that you're trying to monitor too. And the reason I emphasize why it's a defining threat for my generation is that I take a look at the biggest typical pollution problems that we have, and I take a look at something like DDT on the Palos Verdes shelf, if that's, one of the bigger effects, you had a large area that was affected, you had food chain effects all the way up to the eagles going away. You stop that, you come back in 30 years, the contaminants have gone away because they buried themselves or they degraded, and the critters can now repopulate from outside of that 30-mile zone. When we're talking about things like acidification, there's no repopulation from outside a 30-mile zone because you're talking about something that's happening up and down the entire West Coast. And you're not just changing some upper food chain thing, you're really at the core of the food web. So you're going to change the food web in ways that it can't repopulate. So, big one, if I had to focus on one thing right now, I am. That's not what I'm going to talk about today. Because, as I understand it, this is mostly a freshwater group, and this is a swamp program. So let me go to the next one, which is flows. And I'd like to say that of the other three, I think hydrography is really the one we haven't paid as much attention to and really provides some opportunity for new data needs, which is what you asked me to talk about. So let's start out with how is climate change affecting hydrography? Well, it's affected in at least three different ways. First off, you're going to have changing rainfall patterns. I understand Dan Kyan was here yesterday talking to you about that. Dan's as good as there is in the business. I'm guessing that these are the same kind of things that he has already told you. We don't know this for sure, but we know it's going to change. We're probably going to have, people debate whether we're going to have more or less rainfall, but you're certainly going to have more episodic rainfall, bigger events, longer dry events. We're already starting to see evidence of that happening. So, boom, you've got that. Throw on top of that, the temperature changes snowmelt pattern. You're going to see more flow during the winter, even less flow during the summer. You throw on top of that, you've got higher temperatures. So all of these streams, which have more like low flows in the summer, in the future may have no flows in the summer just because of evaporation. You throw on top of that the changes in the demand portfolio. Reuse. We're going to the point that we're not putting as much water into the stream systems because we're doing reuse. This is absolutely a wonderful thing. In fact, it's kind of interesting. I grew up with the National Pollution Discharge Elimination System. The whole idea is we're going to eliminate discharge, and we're going to do all this. We never really did that. We eliminated some of the pollutants. Now we're actually eliminating the discharge because we're doing reuse. Good thing. Except, wait a minute, less stream flow. Conservation. Look at all the success. I live in Southern California. All these programs about overwatering. You can get fines if you overwater your lawns and it runs into the street. People stop doing it. Okay? Less stream flow. Recapture. We tell all the stormwater agencies. Find a way to put out spreading ponds. Get this water into the groundwater. We need it. Less stream flow. So climate change and these drivers. So what does this mean from a science needs perspective? We need to know how does flow affect biota. And moreover, we need to know even what parts of the flow, because in different seasons, you may have more in the summer, more in the winter and spring, less in the summer. Well, maybe for some kinds of biota, that's what they really need. It's what happens in the spring. It happens maybe when they're doing their spawning. Take a certain fish might need spawn, probably less important, but others need it in the summer. You also need to know a little bit more. It's sometimes not about the amount of flow. Sometimes it's about the depth of the water. It's a habitat piece. We haven't even begun to we actually maybe a tiny bit begun to define these kind of things. But that's where we really need to be. And of course, in this part of the state, it's going to differ. You just heard several talks right before lunch, several excellent talks about bioassessment. Are the bioassessment tools we have and the reference conditions established around the right flow conditions? If flow starts to change, well, boom, all of a sudden your reference condition, your bioassessment is affected. So we need climate-ready bioassessment tools. And then, of course, when we do those bioassessments, you got to talk about the causal assessment. What is the interpretation of what caused the problem if the biota is not right? And if we don't understand those flow relationships, then it's hard to say whether it was a chemical or whether it was a habitat or whether it was flow. Okay, this, of course, drives some of the monitoring needs. What we need to do, things like swamp, is enhance the hydrological measurements. We can enhance the number of places, number of times, even the technology by which we do hydrology. When I pick on swamp, I actually want to be very complimentary. Some of the things that my organization, at least, is starting to do, others as well, is do the relationship between biology and flow. The swamp data set is amongst the best in the world for doing that. That having been said, I can also point out some of the places we could do a little bit more of that, a little bit better. Measurement of additional biological endpoints. It's great that SWAMP has focused on that. Honestly, if you have to start, that would be the best place to start. I think Pete did a good job of explaining, why you do that right at the beginning. It's where the contaminants kind of come to. It's the right thing to do. But it's really the right thing to do when you want to look at contaminants. If you want to start looking at flow, maybe you want to do some other things too. Maybe you want to add some salamanders into your program. Maybe you want to focus a little bit more on birds, because the thing that's going to be affected by flow isn't just the flow itself. It's when you get these big flow events in the spring, if they're bigger and larger, then all of a sudden your riparian habitat starts to change, or the amount we talked about. We're not really looking right now at how flow is affecting some of those habitats that relate to them. And then, of course, I need to finish with regulatory part. Okay, how do you tie it back to regulatory? Why do we care about the science need and monitoring need if it doesn't tie back to regulatory? Well, State Board has a very interesting paradox. Let's do more recycling. Great idea. Oh, wait a minute. We got to also protect beneficial uses. Obviously, you got to tie those two together, and it is probably some level of compromise. Unless you have that science, unless you have that monitoring, that's going to be a very difficult paradox. And Steve Moore, I think you all on Tuesday had a whole session on your recycled policy, and the 1211 orders, petitions are absolutely a big part of that. We need to develop the science that puts them in a position to be able to make those kinds of decisions. Dam operations, it's not just even how much you release, it's what season you release, when, how. Again, until we have those flow needs, it's really hard to define that. And then, of course, you've had a number of presentations on cannabis. I think one of our speakers right now is going to be on cannabis, so again, lots of opportunity. So I hope I've kind of whetted the appetite of the next set of things you need to be worried about.
Knocked it out of the park. Thank you, Steve. That was a really, really good segue to the next speaker, and I'd like Jonathan Bishop to then sort of take that ball and run with it in terms of what is the State Board thinking about, how are these programs that typically have worked in their own sort of silos around different parts of the state in their own sort of geographic settings, how do they all come together now under that really nice umbrella that Steve laid out there. So, Jonathan.
Yeah, so the first thing I want to say is we didn't spend $50,000 on insurance. We put that money... Yeah, exactly. So from my point of view, the biggest issue is I can look at lots of data streams, if you like, information about bioassessment, or information about pH, or information about flow, but that isn't going to help me integrate between what the decision is, because the decisions are not about do we have just are we protecting the biotic environment. It's about how are we going to allocate resources between of scarcity. So essentially, how are we relate between how much we're going to protect the common gull in Southern California, or the Delta smelt at the pumps, because if we take more recycled water out of the system to reduce the amount of imported, we protect Delta species, maybe at the expense of Southern California species. And so looking at these things together and figuring out ways to take disparate data and turning it into information and stories that we can actually use in a management context. I used to go to meetings about TMDLs and say, I've got 2 points. I can draw a line. That's all I need. If you want me to do more, let's spend some more money. Well, it's no longer about a line. It's really about a three-dimensional shape that we have to do. And so it's not so much that we don't have enough data as we don't have enough integration of that information. And that's, I think, the biggest challenge that we have moving forward. Sure, we do need a lot more monitoring to answer certain questions. And Steve talked about ocean acidification. I've been asked a number of times about, okay, well, what are you going to do as the water board about ocean acidification? And my first response is, well, what are we actually trying to control? Are we trying to control pH? Are we trying to control aragonite saturation? Are we trying to control CO2 levels? So first, I need to know what that is. Can we actually monitor that in a way that is meaningful, because all of those have diurnal cycles that change, and so you can't pick a number. You've got to now figure out another way to look at that system. So that's the first piece. The next piece is, okay, let's figure out what of those has an impact. And how do we model that direct or indirect effect? And then, does anything we do change it? If those of you that are familiar with the California coast, we have a really productive coastline, and it's because we have upwelling, and that upwelling brings low or high CO2 water, low oxygen up from the depths with a lot of nutrients. Well, is that overwhelming any signal that we're getting from our discharges? We have increased CO2 levels in ocean dischargers, or to spend $2 or $3 billion on upgrading their treatment to remove nitrogen, which reduces the algal blooms, which reduces the CO2, which changes the. I got to know that that's got to actually have some sort of measurable impact, and how are we going to measure it, and how are we going to know? So all of that comes around to this idea that we need to be looking at these not as a single piece of information that we can look at like we do with dissolved copper in a stream and say, if it's over this value, that's bad. We now need to figure out how do we integrate the information of diverse data sets into a story that I can understand. And if I can understand it, then maybe I can convey it to our board.
That's perfect. Thank you, Jonathan.
And I'm apologizing, but I'm supposed to be somewhere else right now, and so I'm going to go do that.
Appreciate it. It's a good way to avoid the tough questions.
Oh, yeah. This is a management lesson right here.
Next time you call me away, okay? Okay, so that's the statewide perspective. We now have two phases of the region, or the regional perspective in the state of California to talk about. And so our next speaker, Jimmy Smith, I'd love to hear your thoughts on how data is engaging itself with your decision-making process in San Diego.
Perfect. Now that Jonathan's gone, we can have some fun, right? I'm going to talk a little bit about how data has informed past decisions, data influencing current efforts, and maybe a little bit about the data needs that we have, but I think Steve covered that pretty well for us. So back in 2001, we got this program, and many of us were very excited because for the first time we were able to collect ambient data, and that was like so cool because before it was all kind of permit-derived data. And that allowed us to launch into some bioassessment work that was being done. The precursor, the Index of Biotic Integrity, was formed, and those scores greatly influenced one of our decisions when we went to reissue the stormwater permit in Riverside in 2010. Heretofore, we had very arduous reissuance processes. Normally took about 2 meetings over several months, and the permits didn't change all that much. But we had bioassessment scores for the Riverside area that told a great story. If a picture's worth 1,000 words, a picture with data is probably worth 1,000,000 words. And what we saw was in the undeveloped areas, parts of the forest and some of the tributary streams, we had good to very good scores. The bugs were thriving, looking great. But in the highly urbanized core, we had fair scores, and the scores were getting worse over about a 4-year period. Our board at the time took that data into consideration and said, we need irrigation prohibition, influencing some of our current issues. So a couple years ago, there was a surfer health study. SCORF was intimately involved with that. And this study found that surfers were getting sick at a higher rate than background after surfing in wet and dry weather. And there was a lot of fecal indicator bacteria out there as well as pathogens. It's kind of everywhere. So the follow-on study to that was to go upstream and start to look for sources of these pathogens. So over 2 storm events, data was collected and looked for HF183, a Bacteroides almost exclusive to the human gut. And unfortunately, they found it everywhere. It was in the main stems, it was in the tributaries, and the patterns didn't seem to make sense. The fact that it was everywhere is what gave us pause for concern. So that data kind of caused us to rethink what we were doing. We had permits that we thought were stringent enough. We had PMDLs in place for Rec 1 and FIV. We were doing enforcement up and down the watershed, and yet still the receiving water was telling us we had a problem. So that caused disruption among us, and internally for about a year we kind of wrestled what to do with that. So finally we are in the process of issuing an investigative order, and that's going out to all the permittees in the entire watershed, from phase 1 and phase 2 stormwater to collection system permits to waste discharge permits, you name it. These guys are going to sit down and actually identify sources and quantify sources, including those from homeless or urban campers, as we call them down there, because they too are changing what the urban landscape looks like anymore. They are now living in our canyons, and there's any number of them living in cars and trucks that don't have sanitation, and they are dumping that stuff right out on our streets, and when it rains, it's mobilizing into our creeks. The data is changing the way we're doing business right now. As you look forward to what we're struggling with, I'm really encouraged to the work SCORP is doing. I think the stuff they're doing with the drivers down to the management actions is going to be key to us. And management actions for us are where the rubber hits the road. Everything from the change in hydrology, well, what's that going to mean for our mitigation sites through our 401 certification program? Are we going to have viable hydrology? Is the hydrology going to wash out our mitigation sites? What is it going to mean for fill applications as people want to armor more? Not only in the channel, now you have sea level rise. And where are we going to put the seawall? And there's a natural conflict there that we deal with too, because the Coastal Commission has authority to protect property, and we have an authority to protect the beneficial uses associated with a horizontal beach. That can come into conflict. So we need to figure out where to make a stand and put up a seawall and to let the lighthouse fall in some places. And that's going to be a tough decision, and data is going to need to help us in that area. Sea level rise is also going to influence a lot of our cleanup. Will they get mobilized back into the aquatic environment at that point? We simply don't know. One of our board's highest objectives right now is to produce biological criteria as a water quality objective. Another leg of the Clean Water Act. We got chemical criteria, but we really want to have biological criteria. And we've got the luxury of a lot of swamp data and co-permittee data that allow the creation of the California Stream Condition Index, which SCORP is a major publisher, the main publisher, I would say. So we're using that as background for our objective, and we think we're getting close. We should be out for peer review within a month or two. But what's going to change when we have a different hydrology set? Are our reference stations going to need to be revisited and recalculated? We don't know. What's the role of other indicators? I think algae shows promise as well for some of our more concrete systems, let's say, as a water quality indicator. So we'd like to figure that out as well. And one of my pet peeves too is let's get a better indicator for safe to swim. We're still now, I think, Ken Weisberg or Ken Schiff can tell it very clearly, better than I can, that I can tell you today what it was yesterday, and if you want to know how it is today, come back tomorrow. And that's not good from a management perspective. We need to know what's going on today, and I think some of the work in rapid indicators along DNA lines to look at libraries of pathogens out there shows great promise for us. So in closing, I think we need to look a little bit differently at how we do our work, and that entails using the data to influence how we use our tools. So looking from a receiving water perspective back, so figuring out what the data tells us about water quality condition, receiving water condition, and then using authorities and our influences to either restore or protect those beneficial uses. And the data will be at the key of that.
Excellent. Thank you, Jimmy. So I've asked Nick to step in and be Jonathan for a second. So give him a moment to sort of transform into Jonathan. Let's go to the north part of the state, and I don't know what time it is, but I won't have any cannabis jokes, I promise. But let's go to the north part of the state, and Christopher, if you could give us a perspective of a particular use of data in and how it's playing a role in your management decisions, or the role of running a program, informing the public, keeping people on target for what you want. So thank you, Christopher, for coming.
Sure. Well, I'll try not to make this a transition too abrupt, because we've gone from very big picture stuff to a slightly more focused issue here. The thing I want to say first, though, is that although cannabis is kind of a focused issue in this panel, it's something that it's an emerging industry that we really know nothing about, which I think represents a tremendous need for data. And so two of the biggest categories I would say that we need to look at is the variability of cannabis cultivation and also the growth of the industry. If we're trying to get a picture of the potential impacts for cannabis cultivation on water quality and in-stream flow in California. So variability, I mean, no other form of ag seems to be as variable from a geographical standpoint in terms of it being grown, in the floor of Round Valley and all the way up into the highest reaches of watersheds in Humboldt. They're, 50-degree slopes, fully forested. So there's that, and then there's the variability in the types of people that are growing and the attitudes that they have towards the environment and the probability that they're going to implement best practices or not. And so as we're looking at data that we've received from the North Coast, we're well aware of that, and we're aware that the water estimates, for example, that I spoke about yesterday, we're getting an idea, but there's still a lot to be gained by knowing who we're dealing with out there. So for instance, just an example, the data I gave, I showed kind of how much water comes from each source, but for instance, people that we go out and visit who are not in compliance already, we tend to see spring diversions that are just dumping water into tanks that are unchecked, and so they just spill out everywhere. And so if we're trying to get a sense of how much water a particular cannabis cultivation site uses, we really need to know kind of generally who's doing it out there and get a better sense of water waste and being able to incorporate that into our estimates. And so that's that's an in-stream flow issue, but there's also water quality concerns that we really need to get a better handle on in terms of knowing what percentage of people out there are doing which sort of practices. So again, we go out to sites, and there's some very clean sites, and then there are some sites where they dump their last year's plant material into creeks. And so to have data on what's in that material, and then have data on what is being transported downstream, the flow monitoring for those sorts of pollutants is something that I know some agencies have begun, and it's a topic that I've discussed with some of you here these past couple of days. But so that's the variability that I was speaking about, but there's also getting a sense of how rapidly the industry is growing. And our biggest need, I think a dire need, is aerial imagery and good aerial imagery, updated aerial imagery that we can use to get a sense of what our concerns are going to be, not just extent-wise, but also the degree to which clustering is taking place, high-density cultivation. If you remember yesterday when Dr. Butzig was speaking, one of the biggest indicators, right, of cultivation is my neighbor growing. And so it's just a sign that it doesn't happen uniformly over the landscape. And so we need to get a better handle on in-stream flow threats and water quality threats so that we can make determinations on a watershed level basis. What is the capacity, or carrying capacity, if you will, for pollutants, and also for water use, for in-stream flow. And so beyond that, I would say just the lingering things that if we're talking about data needs, we need more. We need additional years worth of data. The data that I spoke about yesterday was just 2017 data, and with the amount of variability that we know we receive year to year in terms of precipitation. So the data that I was speaking about followed a historically wet winter. So we don't yet know how water use varies in following drought winters, and so that would be very nice. And then also the fact that we have access to data in the North Coast because we've had a cannabis program for about 2 or 3 years. And so we know what's going on in the North Coast to some extent, but we have now just begun to implement this policy statewide. So to be able to monitor in the same, to get uniform data, I should say, because cannabis is not just grown in the North Coast. It's kind of everywhere. So I'll leave it at that as far as data needs.
Cool. Well, I'll be happy to dive in deeper. That's my job now. So thank you very much, all panelists. So the thought that comes to mind is there's a theme that's come up in every one of these presentations that is how do you integrate data, and particularly biological data with sort of more traditional physical and chemistry data. So, and I know that we have different levels of relationship to this topic across the panel, which I think is great. So why don't each one of you take about 3 minutes to give me your thought on how you see the best use of existing CSCI scores, for the lack of a better argument, that we think as a program are fully baked and ready to start being used in our regulatory programs. How do you see, each one of you, the role of that data being the most useful to achieve your mission? And we'll start with Steve. You look ready.
Sure. So I guess my starting point would be, first of all, I love Pete's presentation because he was saying, the essence of his presentation was the science is mostly baked. It's now ready to move to the next level. So I'm interpreting your question in part, what are the pieces that are keeping us from getting there? So Pete has some of them in his presentation. I'm going to elaborate because I think there are a few more as well. So I think it's not the science. I can always tell you it's science that will give us incremental improvement, a few things we could do better. But I honestly think it's really the policy decision impediments at the moment. So Pete brought out one, and Marcus followed with a presentation on the one of how you set goals. And people don't want to accept this as an assessment tool unless the goal is a fair goal. And when you've got a concrete line channel and trying to say the goal is to get back to the same thing as you have in a unlined channel, well, that's a tough one. And so the tool's moving along there. One that was not talked about that I think is equally important, maybe more important, again, for trying to get the community to agree we're going to use bioassessment, is figure out how you're going to use it. Is it going to be used in place of chemistry or in addition to chemistry? So if I'm a wastewater discharger and I'm told, well, you've got to do chemistry, but you also do biology, I've just got one more thing that's out there that I've got to be concerned about. So I don't want it. On the other hand, if I'm being told, well, wait a minute, the biology is what you want. If the biology is in good shape, can I not deal with this chemical measurement that was taken at one site 3 years ago? There was a point-in-time measurement, and I can no longer have to worry about that because the biology, in a sense, trumps it. Alternatively, what happens when I've got biology that's a problem, but I don't think it's due to something that's a chemical. I'm a discharger. It's not due to anything I discharge. It's due to the fact that somebody came in and cut down all the shade in the system, and it's too sunny and it's the water's too warm for the kinds of bugs that we would want to exist there. I think we've got to figure out, how we're going to use it. And those are, again, it's science-informed policy, but it's definitely the policy part. I have my own feelings on how I would do that if I were in those circumstances. So I think that's actually the biggest impediment. We've got some tough choices. Jimmy's group is starting to make those choices. I think that may be a great precedent. Because I think Jimmy outlined how he's going to use the data. I think these are some of the impediments. I'll throw one other impediment out there, and I guess that's capacity. We've got to get the labs all doing these kind of things. We don't have enough labs right now to make this widespread.
Is there a technology innovation like that? DNA for
well, that's exactly where I was going to go, Greg. We're on exactly the same page. Is that I think there's two pieces of it. I think one, for doing the traditional things, we've got ELAP, which is getting very capable right now, and they're willing to take on new things. This would be a new thing. There's got to have to be a process to make sure that people are all doing it the same. But I think eDNA in particular, or DNA in particular, not necessarily even the eDNA, but is another thing, because that's going to cut down on the cost, it's going to cut down on the time. I know, for instance, when you're doing things like stream algae, there aren't enough taxonomists, but moreover, we've done studies looking at how consistent the taxonomists are. It's not consistent. And then you've got a third piece, which is the wait time. it will take you more than 6 months to get a sample back. The DNA approaches, I think you can get the same answer. You can get probably an even better and more consistent answer. Greg Schimmer hit up on a number of the things that need to be standardized, but I think you get a faster, better, and cheaper answer. We have to develop those.
Okay, Jimmy, so you obviously don't have any impediments because you are moving forward. So let's hear what you did to knock them out of the way.
Well, we're not done yet, but in some ways the regions are like the states are to the federal government. So if the state board would let us go out and maybe experiment a little and be innovative, if you will, and to develop some biological criteria, and let's see how it rolls out, right? Not talking to anybody, in particular in the third row or anything.
Should we give him the scissors that he can run with now?
So the Clean Water Act, right, it calls for physical, chemical, and biological integrity, and heretofore we focus so much on chemistry. And when it comes to certain beneficial uses, chemistry simply isn't that great. You're looking at a snapshot in time and how it may influence the ecosystem-related beneficial uses. You're looking at toxicity that has all the challenges of proxy animals in a lab condition. But with looking at the bugs, we have a direct measure of the use itself. And so for us, it's very exciting. And we want to put it in as a full-blown water quality objective. And we think it'll be very transparent in that way. We're already using it in some of our 401 certification programs to look at what the downstream water quality condition is before and after impacts and before and after a mitigation site. We know enforcement, it's a great tool if we have a point source spill as well. And how it relates to chemistry right now, I would like to see permits roll back on some of the chemistry. Certainly we still need to protect human health, so some of the fecal indicator bacteria and anything that may impact human health directly, we need to be monitoring chemistry for. But if we're talking ecosystem uses, let's be more adaptive. Let's look at what the biology is telling us. And if we have problems then, using causal assessment and some of the other tools we have, then let's start to look upstream and to see what the permits are doing, see how the water quality looks upstream from a chemistry basis. And if we find some reason then to crank down on a permit or to even change some chemistry water quality objectives, then we're doing so based on a known impact to the actual biology. So I think we could do less chemistry, but do it in a more adaptive way if and when we have a biological criteria in place.
Okay, so we're getting down towards the more controversial end of the table. So Chris, I'm going to throw one at you that's kind of the same question, but I'm going to say, can you opine on the use of biological assessment data, bioassessment data, in-stream bioassessment data in context of using it for a particular case management, like enforcement of a case, and I'll just say riffle, just target riffle kind of an approach versus a stream reach kind of an approach. And how do you see the role of biodata in your program, Eyes?
Well, I mean, until today, I hadn't really considered it. It's definitely something that, in conversations with our friends at CDFW who are working on the same things with us, yeah, certainly, I think they'd be more familiar with using bioassessment data. But from our standpoint, like I was alluding to before, we don't necessarily have a good way right now to estimate the impacts to water quality that we see from cannabis using flow measurements necessarily to that extent that it would be beneficial, I imagine, to have some sort of bioindicators that would allow us to, for instance, look at maybe not even individual sites, but slightly larger watersheds and the access. One of the issues with studying cannabis, is you might imagine, is it's very remote places, and access is an issue, both logistically and safety concerns. And so to be able to be a kilometer, 2 kilometers, 3 kilometers downstream of where you're actually interested in would be tremendously beneficial. So I think that would probably be the biggest boon to using something like that.
So Jonathan.
Yes. I apologize for storming out. About to speak. And this topic is close to me in my previous roles. When I ran the program for the water quality assessment, which is the 303D and 305B report, I saw CSCI and biology in general as a real opportunity for us to be proactive rather than reactive. It allows us an opportunity to not only identify necessarily those waters that have impaired biology, but also identify those that have great biology and should be protected. And also, we heard some presentations by Marcus Beck about how we can use these models to prioritize. And I think that's really important. We need to be thoughtful of how we think about our monitoring programs in the front end. If we can prioritize, okay, look, we have some questions to get the most bang for our buck, that's going to result in positive happening, that not be able to be restored. I also see when I was working on the biointegrity, biostimulatory policy, this is a big topic. I think this is an opportunity where we can take the CSCI scores and overlay them on a stressor gradient, try to get to better determine what is that causal assessment. We're trying that out with biostimulatory, which is eutrophication, nutrients, big topic. How do we set objectives for nutrients like nitrogen and phosphorus, the protection of aquatic life? We're talking about a level of 0.1, which will freak out any sort of discharger, but we need to be able to show with some sort of confidence that, look, the biology is being impacted by the eutrophication and not something else. So I think that Steve makes a good point that the causal assessment, as the Jimmy, that causal assessment's got to be a part of it. We need to take that next step where we look at several stressor gradients, and I think a potential way to do that, we have a kind of an approach or framework already set up with how we use the sediment quality objectives, where we take a multiple line of evidence approach, where we look at not only the biology, but we combine it with the chemistry and the toxicity. So we saw presentations from the spot and toxicity as well, where if we combine these data sets, we can get a really good picture of what may be or may not be happening here. So you take the biology, okay, maybe this biology is scoring low. Okay, is the chemistry, what's the chemistry? Yes, it's not really there, but we still got toxicity. What's causing that? Or vice versa. It could be flow, it could be something else. But the more we can be clear and transparent in how we are thinking about regulating an entity, the better it will come off. A lot of this is communication as well. We're trying to message this in a palatable way. Some people don't understand CSCI. We've been working with SQUIRP to develop a biological condition gradient, which is another way of kind of showing the same information but in a palatable way. And I think this symposium is kind of playing on that. How do we take data that maybe not palatable to a widespread audience and turn it into something that can be digestible, using visualizations, thinking outside the box to really play to somebody's, for lack of a better word, heartstrings, to really get them to say, there is value in this, and this is really informative on how we make our decisions. So I think it's pretty baked, but I'd like to see a better integration with causal assessment.
So speaking of heartstrings, if anyone finds my tea, it's somewhere in the audience, and just let me know. Christopher, the relationship I have with North Coast, goes back to I grew up there, but I also studied up there, and I know that the map that Calvin and others have been showing shows a lot of really good reference data on biological condition. And you mentioned access and safety. Is there technology innovation that you guys are thinking about that might allow remote sensing data to help inform on the cannabis question?
Well, I mean, at this time, it's just a matter of reviewing aerial imagery, and we are working on techniques to improve that. We are attempting to use image recognition analysis to improve that search process.
For spotting and grow areas, or for looking at water, or
for detecting cultivation.
Yeah.
The other alternatives for remote sensing, no, there's not a lot of other data we're trying to that we have ambitions to.
Is anyone looking at deploying measurement devices like flow, combination with other probes, and sort of like to optimize some of these operational decisions that might come down in those water jets?
Well, sure. I mean, there's flow gauges, and there's flow studies that we're working on, and I know there's flow studies that Fish and Wildlife are working on. I don't know how much they'd want me to talk about them just how much I understand them and to say exactly what they're doing.
Well, maybe we can have a future, like, whole panel discussion on some of the innovations, because I think there's a lot of good energy in the cannabis world because of the need. There's a huge stressor driver coming at the state of California, and this remote access safety condition is universal.
Yeah.
So.
Yeah, and we've spoken, or we've had people suggest, well, why don't you use drones? And for the most part, people are scared of Big Brother enough out off the grid up there that the idea of flying drones over them might just be the straw that breaks the camel's back.
Right. And they have shotguns, right?
And they have shotguns, yeah. Which it doesn't take much to aim a shotgun. Yeah.
Okay, so now I'm going to open it up to the audience, and if my staff with microphones could be ready. Does anyone have any questions for our distinguished panel? Jesse up front. Great.
I have a question about, I guess I'll ask Jimmy, for the physical habitat index that's currently being developed. I know you guys have looked at using STEM scores, and I think possible EHAB metrics, I'm not exactly sure which ones you're using, but there is a physical habitat index that's almost completed. And I'm just kind of curious how you think that might factor into helping to answer some of the questions about whether or not there are physical habitat alterations that are likely contributing to lower scores or water bodies, and how that might play into some of your information options.
Sure. Eventually, we want to get to physical integrity of our watersheds as well, and I think that's a long way off for many of them. As Nick pointed out, our priority is some of the better quality streams right now, and how do we protect those? And we kind of got to separate in how you apply a CSCI to a highly modified stream to a more pristine stream. And in our mind, it's very distinguished by the fact that if you're not meeting a biological condition in the waters, it doesn't mean that the discharger is necessarily out of compliance. And we're trying to draw that distinction and kind of get away from that argument of what the habitat necessarily is doing to it. Right now, you could probably make arguments and back it up with chemistry data along the lines of DO, temperature, pH, that concrete line channels are not meeting their objectives. But we're not seeing any enforcement along those lines. We're not seeing any third-party lawsuits along those lines. We realize that it's the habitat. But I think really making that disconnection between the water quality condition, not necessarily the receiving water limitation, but the water quality condition being different than what the effluent limitation and the permit requirements are, will help us get over that hurdle.
Any other questions? Okay, well, with that, thank you very much. Oh, sorry. Yeah, sorry. Thank you.
I'll throw one out. We've talked about climate change. We're talking about landscape. We've touched on the edge of flooding. And about using data and management. And from
maybe we can amplify that. First off, absolutely correct. I think, though, there's almost like multiple different types of uses. I think, taking an example, swamp, which I think is really what initiated this symposium, a lot of what swamp is doing is in the realm of the 305B assessment, the prioritization. So it still has a very clear decision support. But then there are other types of decisions. So for instance, the next level that I go to is I think about modeling. Because modeling allows you to play out, as you say, scenarios. And so I talked about flow as a for instance. One of the things that you want to be able to do is you want to be able to build a model that says, if the rainfall changes in this way and the flow then changes in this way, the bugs will change in this way. Or if you remove, go into some very critical decisions like 1211 waivers. For those unaware of 1211 waiver, I had it on my slide. If you're a wastewater discharger who wants to do reuse and you're no longer going to discharge to a water body, you have to petition the state for a wastewater change order that allows you to reduce the discharge. Well, we need to be able to do the models that say, if I reduce it by 5%, what happens? Reduce it by 10%. Or if I do it in this season, 10%, what happens? Versus if I do it in this season by 10%. Right now, SWAMP is not organized around exactly those kinds of models. So it's been incredibly helpful in building those models because they have data sets that nobody else has, and they have them at the statewide scale. But on the other hand, at some point, you have to start to go, have we achieved our 305B, and start to prioritize what are the models you might be tweaking the data collection to optimize. And I think it's very doable. I think the hard part is anticipating all the right questions and which you need to do the model.
Yeah, and I just want to thank you for that feedback. This is exactly why we have this symposium, is to try to improve the connection of the people that are generating the data, using it for maybe their purpose. Maybe every year we get a little bit broader in our sort of community of data ecosystem, so to speak. And part of the problem is getting the right audience to the table to give us what are your user needs, quote unquote, from a data, technology lingo. Like, what would a decision support tool look like for you? It may be very different, as Steve points out, than another person that's in the audience. Organizations and the data. They just haven't really got into it and gotten dirty with it, so to speak. So any other questions from the audience? Eric.
Yeah, thank you. I often hear from decision makers that it's really lovely to have all this data that we have available to us, but what does it mean? And the feedback I hear is it would be great to put it in some type of a report card that tells you what that watershed health is. I'm curious, from your point of view, what would that report card look like?
Well, let me jump in on that. We've taken the opportunity now to do water body fact sheets. It's both swamp data and some of our other data sets that come together and have a two-pager that really says what is the state of a use within a water body. And we find these to be very effective tools to convey a quick message of what's going on, not only for the general public, because I think that can help them change behaviors, and ultimately we need them on our side if we're going to make any kind of changes, but also to some of the regulated community that we deal with when talking to cities and counties, and maybe even to state legislatures as well. So if we can convey all that data and package it into information, now we have something much more powerful. So I find that very useful. For us, at a board decision, I shared the example about Riverside County. Our board is very interested in seeing the data and having it kind of explained to them from multiple perspectives. They will challenge dischargers. We had a classic example where there's a report that Squirt put out, and some of the dischargers didn't like the findings on a fish consumption study. So our board asked these guys, well, go do your own analysis. And they had to come back about 6 months later looking at that data and trying to make their own interpretation. And it actually made the process better. There are a few little tweaks that needed to be made to the report that were some loose ends to tie up. So the process was better, and then I think the decisions in the future will be better based on that report. That's just one example.
Yeah, I would say that you can see some similar examples of that in the Central Coast. Region 3 uses their CCAMP data set to generate report cards using beneficial use support. Green means it's supported, yellow means maybe insufficient information, red means it's impaired or not usable. And I think that can be very helpful in messaging. A lot of this is in communication and messaging, taking data and making it useful information, and then hopefully turning that into knowledge. And I think that the key to that in providing a real-time, useful data, that's part of it, is that we have the data in a format that's machine readable and then it's updatable. If it's been seen, then we can put it on opendata.ca.gov and then transform that using some of these visualization tools and turn it into report cards as needed. It's just about making sure that data is available in a high quality form and then as current as possible. Once we have that data, then we can develop, what are the right indicators to determine stream health. We have a Healthy Streams partnership as part of the Water Quality Monitoring Council that other attributes to really identify, okay, where are the good streams, where are the streams that need help, and where are the streams that we need more information. So I think it's right for that, and we just need to think about it.
Anyone else? I think that's a great segue to the actual unveiling of our water quality status report, which is meant to be a way to tell the report card on the state of California's water. We've talked about this for a few years, at least in my experience in OEMA, and each year we're getting better. So I'm suggesting that we have like a shortened break instead of an extended break, a 15-minute break, and then everyone come back here and we'll have the unveiling of the water quality status report that'll answer Eric's question of how do you tell the story.
All right.
Okay, welcome back, everyone. Grab a seat or stand if you want. No judging. Those of you who made it to the end of this, thank you very much. You'll be rewarded with a really cool reveal of this year's data story map, water quality status report, whatever you want to call it. The background of this is I came on board about 3.5 years ago, and prior to that, the Office of Information Management Analysis has that name. It's not called the Swamp Office for a reason. It was meant to be a place to start taking some of our attempts to gather information and data and integrate it with other stuff and turn it into something that becomes more informing and eventually knowledge to the organization so that we can make steps to move forward. So what I and my team have done in the last 3.5 years is really focused on how do we do that. You notice this is a very swamp-driven, swamp-centric kind of an event, but it's also meant to sort of bring in other voices, bring in other perspectives, and to eventually try to wrap this data up into some sort of a structure or format that looks like a status report for the surface waters of California. And maybe eventually we could even start talking about the groundwaters of California. So this is the second year we were able to pull off an actual data story. Last year we revealed a really cool one that had individual stories that sort of appeared. They're still on our website. They're extremely useful still. I still use the harmful algal bloom one to tell people this is basically what we're dealing with, and here's links to live data. And so these story maps and these abilities to sort of use tools like that to communicate the data in ways that's better for the consumers of the data is, it's not unique, it's not novel, but it's unique to us, and we're really trying hard to do it. So this year I really raised the bar and I challenged the team to get more collaborative and get more narrative. And so what they were able to do, and you'll see the team here in a minute, was to expand the membership of this team and to really focus on what is the story, what are we trying, how does this weave together in some ways, and still allow people to dive into the specifics of the data visualizations and the data itself and interact with the data. So this is really a huge accomplishment in my opinion, and I really want to thank the whole team. And especially I want to thank Michelle Tang and Nikki Hack, who sort of pulled this together. Lori Weber really helped too in sort of her transition to her new job. She was very careful with this baby and sort of handed it over and said, this is what I think Greg wants, good luck with it. And you guys have done an amazing job. And so I really want to thank everyone for that. And we will reveal it here as we start introducing the people on the team. So the first one that Marcus Beck, come on up. And Michelle Tang is right here. She's already up here. So thank you, Michelle. Marcus Beck. Rebecca Nordenhall from the San Francisco Regional Board, I believe.
Great. Give it to Michelle.
Oh, yeah, sure.
Sorry.
Thank you, Michelle. Hi, everyone. I'm Michelle Tang.
report. We have the people who created the data visualizations that kind of make up this report kind of lined up here, and they're going to quickly go over their visualization, kind of give you an overview of what it is, how it works, maybe the process that they use to create it, and then they're going to sit down and we're going to start the panel. So I'll go ahead. So the report is actually an ArcGIS story map, and inside the report itself we've embedded the visualizations that each person has created. And then so we're just going to go ahead and kind of go one by one through them. So the report is kind of divided into different sections. It's, the theme is kind of a land to sea connectivity, and we're looking really at the monitoring efforts that kind of fit into each kind of a water body type. So starting kind of with the land, where we see runoff, seeing it kind of travel downstream into lakes, and then finally into the ocean and kind of our estuary systems. So, so first up, kind of in the land section, we have Bryn Phillips, and he will come up and talk about his map.
Okay, this happened last year. They made me go first, and we stumbled through it for a few minutes, and it seemed to go well, I think. I'm not sure how this is going to work this year, but it's because it's a different format. Last year, that each contributor had a standalone chapter, if you will, and now they're all kind of lined up in, like Greg mentioned, like a narrative, and it's pretty slick. And I'm assuming this is all done in Tableau, right? And Michelle and Nikki were awesome in being able to put this together just from an idea I had and a quick data file that I sent Saturday morning, just a few days ago. And you guys saw the spot talk earlier, or hopefully most of you saw the spot talk earlier. It was this morning, seems like a lifetime ago. And so I showed some data that was basically the mortality data of our spot stations with the toxicity testing that we do for our watershed monitoring of the 100 watersheds in California, and I juxtaposed that against some pyrethroid toxic unit data. And toxic units are a way of normalizing a chemical to the potential for that chemical to cause toxicity. And with pyrethroids, they're additive. So if you have bifenthrin and cypermethrin and permethrin, and you can put them all together, and there basically will be additive toxicity. So there's this cumulative effect, and you can sum those toxic units, and you can look at that bubble on that right-hand map, and you can get an indication of how much toxic potential there is from that class of chemicals. And so I had this idea to put these two maps side by side and have this tracking bar at the bottom where we can just click through the years and just kind of have this visual. I'd hoped to actually create this as part of my presentation earlier, but I didn't know how to do it. And it's this program's really powerful, and the water board and Michelle's group and has really been instrumental in kind of helping to create these things, create these pictures that help communicate things. But I just wanted to sort of scroll through and give an indication of how these things track year to year, because as I mentioned this morning, this is kind of the crux story of SPOT, how we have these links between the observed toxicity in our water bodies and the concentrations of pyrethroid pesticides, at least for the organism Hyalola azteca. Can't quite see whether I'm pointing at the arrow, but the cool thing about this is the large dots track with the large dots more or less year to year, and so it's a good visual depiction of how the data are tracking. And we'd like to do similar things to this for the other data sets that we're gathering as part of SPOT. Our most recent data set So it looked a little different on my phone. But, you know, it has our different land uses, and there's another couple of figures that are associated with this particular part of the story, and it's the pyrethroid trends and the median some metals trends that we're seeing over time. You know, these are significant trends both urban and statewide. And so the linkage to the urban land use is the point we're trying to make in this part of the narrative.
Okay, and next up we have Louise Dessa, who's going to present on his visualization of irrigated land toxicity data.
I had a problem now. I cannot see. Okay. We have a large data set for irrigated land statewide, but it is sitting there, so we want to show it how it is based on the toxicity level. So we downloaded the data from CIDR and categorized it into magnitude of toxicity. As you can see there is, so I downloaded the data from CIDR and created two different magnitude of toxicity for irrigated land for statewide. The reason you see Central Valley irrigated land toxicity only, it tended up because of the screening process. So when this data was posted to the open data portal of California, there is a quality assurance classification. So based on that one, I selected the best one, Central Valley irrigated lands, was the one who has complete data set. That's why it ended up like that. Otherwise, I started off with statewide data. So as you can see in the dashboard, there are three frames. You can say it frames. The map, there is a bar graph, and there is what's that, filtering tools. So based on this one, you can choose any one of it you want. For example, if you want to look at high toxicity side, you can click on that one. Okay, that one I think I replaced it. But if you if you want, you can pick a side from the map, or from the bar graph, or from the pull-down menu here. For example, if you choose this side, if you want, you will see the result of that one, like moderate toxicity. But you want to see for all of them, you need to come here, and you pick it up like that. You will see all samples collected. So the middle one that shows you is the site, the year it has been collected, what kind of species has been tested, and the results, if it is water or sediment. And as you can see, it will also show you the number of samples. Basically, what you have in the database is translated here visually. That's what it is. So you can choose this one based on year here from this one. You can choose based on years like 2012 if you want. So you will see all the results for 2012 like that. So if you want to choose based on the species, you can come here and pick the species. Daphne, for example, then you will see all the results right there. So anybody who is interested in its own creek or river also can come here and pick any of the creeks. For example, you can select Anderson Creek. Okay, it is a little bit slow. Let's do this. The reason why we didn't see the result is because Anderson Creek is started sampling in 2014, but the selection was 2012. So this is how this data set is formed. So it is basically easy and anybody can come and choose and select whichever size it is. So I think that's all.
Okay, so next up we have Rebecca Northwell who will talk about post-fire water quality monitoring in West San Francisco and regional water boards.
Hi, thank you for having me. So as everyone I'm sure knows, we had some devastating fires in the North Bay last winter, and so as part of that effort, we did storm monitoring to see if there were any negative impacts to water quality following those fires. So we collaborated with Region 1 and built study designs that were pretty similar, and so this is a data visualization tool that I made to complement fact sheets that we developed that are available on the San Francisco Bay Water Board's website. I encourage you to check them out because they've got a little more information on the study design and the flows that we were getting during the storm events and whatnot. But basically, this is a map of our sampling sites, and so that we had, it's important to note if you're not familiar with the regional board boundaries, the Tubbs fire was predominantly in the Region 1 water board, so I'm not referring to the Santa Rosa fire. Everyone always asks me about that, and that's not within our jurisdiction. But so we have the Atlas of the Nuns fire, so the Sonoma Creek watershed and the Napa River watershed. And so basically this tool allows you to click on a site and I'll highlight this data for you, where you could say, I'm only interested in, the Sonoma watershed. You could search, filter. So it's just a tool to let you see, basically, if you had any curiosity about what we found, and I'm happy to report, surprisingly, we had very few exceedances, less than 2%, and they were all chronic exceedances, so happily no significant impacts to water quality. So, yeah, play around. I brought copies of fact sheets if you would like to see one, let me know, I'll give you a copy. Thank you.
Thanks, Rebecca. Next, we are moving from the land section and we're going to the stream section. Okay, so back on the stage is Calvin Yang, and he's going to talk about his bioassessment regional snapshot visualization.
Hello again. So this is cool. This is maybe better than the slides. So just to give a general overview again, so this dashboard was meant to just summarize all the statewide bioassessment data that we have from the PSA and the RCMP. And the goal of it was to make it so it's a statewide data set, but how can you make it more accessible to the regional boards? How can they look at the data from their perspective? And so that's what the goal of this dashboard was. Just to make the statewide data set more usable. And so you can click on this map here or zoom in if you want to look at a specific region. And is Jeff out here? Well, I can click on the Colorado River and you can zoom in on where the sites are for Region 7 in terms of bioassessment. And there are reference sites in Region 7. And each of these sites, which I didn't go over in my presentation, they do have pop-ups if you hover over them, so you can know more information about the site, what's the name of the site, what land use is it, and the site code and the name of the station. And then there's different, here's a legend just showing what the different colors and symbols mean. And then there's the checkboxes where if you just want to look at just reference sites, you could see quickly just reference sites on the map. And just to show you how that looks, you could see on the summary table, so, oh, you can't see it, cool. So it's showing 51, but then as soon as I turn on probabilistic, then there's only 47 results. So it is instant as compared to the slides I was showing earlier. And then if you want to go back out to the statewide, you can just go back out on that map. Oops, this map, yeah. And then you can see that there's nearly 3,000 results for CSCI scores. And all the different parameters are listed out in the summary table. So we have nutrients, we have chlorophyll A, ash-free dry mass, turbidity, conductivity. And then at the bottom is the bar graph that displays all the different results by land use. So if you want to look at CSCI, this is all the median values. And then if you want to look at phosphorus, you can see what the difference is between land uses. So as you can see, urban agricultural land uses tend to have higher phosphorus values. And it looks pretty good, it's pretty instant. And if you just want to look at just one site, you can click on one site and it'll show what was collected there. Thanks.
Thanks, Calvin. Next up, Marcus Beck is returning, and he will talk about his STAIN tool.
The tool is bringing the scientific results to people that are going to use it to make decisions. And that's really all of the essence of what this is trying to do. We actually used this app during the entire process when we were working with the stakeholder group to, one, again, help them understand what the models were doing, how they were working, but also to, and more importantly, use the model results to help them develop priority recommended actions for their locations. So this is an app that is hard-coded for the San Gabriel River watershed, but that doesn't mean we can't apply it elsewhere. So a plug I want to make here is that we can plug in any watershed here in the state of California and populate the results to use it in a context. So I'm just going to kind of walk through the different pieces here. We tried to set it up in a logical way to where, there's this landing page that they get to that sort of explains all about what the app does, how to control the different features, as well as some definitions of what we mean by classifications, constraints, expectations, all that good stuff. Because if you remember my talk, I went through a lot of the assumptions that are made going into this. So it's pretty, I think, good to be upfront with what we mean by priorities and constraints and all that stuff. So once you go through the landing page, the first tab here, so there's 5 tabs you can go through. So the first one is basically just showing what the scores are like in the watershed, what the observed CSCI scores are, what the reach classes are, and then what the site expected score, or what the observed scores are relative to the expectation. So these 2 maps are linked. This left one shows all of the actual CSCI scores by reach, so you can see what the site was, what the CSCI score was, and then if you hover over the actual reach itself, it actually on this left map, you can't see it, but it actually shows the most likely score from the model, so the median expectation. But switching over to this map, the reaches are now coded as the actual classification as likely constrained, possibly unconstrained, and likely unconstrained. And then the points here, once you mouse over those, they actually show the score relative to the expectation, so over or underscoring or as expected. So this first set of maps is just to get an idea of what's going on. And then there's actually a tabular summary, or actually no, this is the plot that I had in my talk showing basically the CSDI scores for each reach plotted against the range that you expect for that particular reach where the score was measured. And I like to show this one because we can take away the context. And now you're like, oh, dude, I don't know how to manage these places. You can put the context back in. So this is like our, you know, what we're trying to do. There's also a tabular summary that just gives you different numbers of which, how many stream classes are in the unconstrained or constrained classification, how many sites are scoring above or below or as expected given the classification. So it's just another way to look at the results. Now the real cool part is this tab where we actually, if you remember from my talk, I had that figure, well, this exact figure here that shows all of the possible ways the site could score given its reach expectation and also where it falls given the potential biological threshold you might want to look at. And so it's pretty cool right here where we actually give the user the ability to choose for this particular reach type what recommended priority action you want to pursue. So remember, they can choose to either investigate and or protect and or restore. So one to many or recommended actions, again, on top of routine baseline monitoring and management. So we're not giving an answer. We're giving the users the ability to define the answer on their own based on how they think the site should be treated based on the expectation. And then the final piece is the maps that show where those sites kind of fall out. And based on what's chosen in the previous tab for the different scoring possibilities, that just propagates to the map itself. So you have 3 different maps showing the 3 different recommended actions where they fall in the watershed, and this is, you put in your pocket and say, now I actually can make an informed decision or more informed decision from these results. There's 2 sort of take-home messages. Well, one main message. This is not just a map to view results. This is a decision support tool, and I'm not saying that as a buzzword. What I mean specifically by decision support is we have not hard-coded anything in here that leads the users to a particular decision. So we're giving them the option to explore different scenarios based on how the model is set up. So I haven't actually talked about any of these sliders at the top yet, but these are key decision points where these define basically how the reaches are assigned to a class, how certain you want to be in the model results. And so we've given the user the ability to sort of toggle this information. So this slider right here actually narrows or increases the range of scores you want to use to define your reach classes. And so you can see it just switched there. So in this case, somebody might say, I need more certainty in these scores, and they can sort of narrow that to their desire if they want. Same biological objective threshold. We've given them the ability to change that up or down based on a more relaxed or a more conservative approach to defining potential impairment. And anytime these are changed, the effect propagates to all of the tabs on the app. So it's interactive in that way, and we've definitely set it up to let the user explore on their own to sort of come to the best approach that works for their particular location. So that's it. Thank you.
Thank you, Marcus. Okay, so now as we move down the watershed, we're moving from streams to lakes. And Stephanie Scott will present on her visualization about the status of nutrients in California waterways. Her visualization actually covers both streams and lakes, but we put hers in the lake section because it was a great transition piece. Hi, I'm Stephanie. I work for the SWAMP program. And so my visualization, I took all of the nutrient data that was available in CEDA and created this map just for exploratory and informational purposes. It actually came out of a request that Lori Weber had when she was my supervisor still. She was just curious to see what we had in terms of data. And so just to kind of walk through this first map right here, it's all of the nitrogen and phosphorus data, and it's more specifically it's total nitrogen and total phosphorus only. There's other nitrogen and phosphorus analyzed in the CEDA database, but just to keep it simple, we just chose those two. And yeah, so these show just the median of all the data different spot, and if you wave your mouse over the dot, it comes up with the monitoring site name, as well as how many samples were collected there, and the median. Right now it's set for calculating the median for all the years that the data goes through. And so for this database, it shows in the title. It goes from 1999 to 2017. And then up here, this little slider, if you click, it'll show just the median for each year and the number of samples. So in 1999, only had one sample. But as we go on, more appear. And then if you notice, the colors also change too. So it's recalculating the median level of total nitrogen, total phosphorus for each year. So this goes all the way to 2017, which is the latest data. This is all of the data just together in one scatter plot. It's on a logarithmic scale because the data was actually in a very wide range. We had a lot of data that was like 0.01 all the way into like over 1,000 milligrams per liter. And all of these samples, they're in milligrams per liter. And so it's just, I just thought it'd be interesting to also see like, if you could see like an overall trend from all of the data in California. And this one also has the option to see nitrogen and then also phosphorus, like on a separate scatter plot. And this plot, it also includes the sensor data that we had in the database. So these lighter colored ones, like either means, so like this one, it says detected, not quantifiable, or DNQ, meaning that the machine was able to read that there was a level, but it's not the most accurate reading. And then there's also non-detect, which is below the reporting limit. And for this graph, I just put those data points as the reporting limit divided by the square root of 2, because I heard that that was the substitution method, and I thought it would look good for the scatter plot, just to see like the range of the data that we have. So, and then this graph, this map, it shows the trends that we have of the nutrient data throughout California. So on the right is nitrogen, on the right is phosphorus, the left is nitrogen. And this one is color-coded by the trends. We calculated the trends by calculating the Kendall's tau coefficient, which is used for data sets with sensor data. And just a thank you to Nikki Hack for helping me out with that in R. And so for this, even though there's a good number of sites where we could see like, oh, is there an increase or a decrease over the years in which we've collected the data. If you click on this bubble chart, it'll filter it out, and it shows that actually most sites, we don't have enough data to really determine a trend. So I think it just shows the importance of continuing to monitor and to add to CDN, and also making sure that it's like good quality data too. I also filtered for the data that has like the highest QC ratings, just to also keep it more simple. So, and then the last slide that I have is just it's just a breakdown of seeing like which programs have submitted data to the CDN database. So it's just kind of interesting to see like if one program has the most, and then irrigated land. Yeah, and then it also will show you like how many of each nutrients like the program have monitored for. And I'm sure that that is based on like the goals that each of these programs have. So yeah, some of them are, it varies a lot in terms of region and how many. All right, and that's it. Yeah, thank you. All right, thank you, Stephanie. And next up, we have Jay Davis, who will present on his data visualization on the Clean Lake study.
So SFEI decided to complicate things a little bit and pitch in and develop the visualization part for this story. And there was a hiccup, and our story isn't, all the pieces of it aren't in here yet. We're going to fix that shortly. Quickly, but I'll just walk you through what the story is. And in 2014, the bioaccumulation monitoring program for swamp decided to try to focus on the 10% full part of the glass for fish contamination and look at clean lakes, look at the cleanest lakes. And there were a couple of objectives of the study. One was to go back to lakes that had been sampled previously and had low concentrations and confirm that they still have low concentrations. And then second, to try to see if we could help understand why these lakes had low concentrations. So for the first part of for that first question, we picked the cleanest lakes that we'd seen in prior sampling and went back to them. We did confirm that these lakes have persistently low concentrations of mercury and PCBs. And the first graph in the data story shows a histogram with all the data based on using largemouth bass as species and showing that indeed these lakes are really at the bottom of the distribution. They're in that bottom 10% of the distribution. That's what I'm talking about, a 10% full part of the glass. And then the next part of the story is showing where these sites are. And one of the things we always want to do is highlight the Safe to Eat portal for the mywaterquality website. And one of the things we wanted to do with the story, and one of the reasons we wanted to do the programming on the visuals, is because we wanted to basically link to and use the functionality that's already in the portal. So this is a map. This is basically the data and trends page from the portal that we're accessing through this story. And it's a great mapping tool, and then you can click on each dot and get the latest data for that location. You can look at the trends for that location, And then you can also print a report that's intended to be something that anglers can use to get all the data for that water body, for nearby water bodies, and point them to advisory information. So it's meant to be something you print out on a page or two and take with you when you go fishing. But the interesting thing is that there's a geographic pattern where the low concentrations tend to be in the southern part of the state, and especially the southeastern part of the state. This is one of the places where Region 7 gets spotlight. And so this points to some common conditions that these lakes can have that might explain why they have these very low concentrations. Fortunate that U.S. work, but unfortunately, we weren't able to answer that question. The story includes a cliffhanger because we weren't really able to explain why these lakes have low concentrations. I think we took a step forward and kind of point to a better design that would be able to do that, but that's something that we're going to have to try to figure out in years to come. And then the story ends with always the important message for public health is that, yes, we have a severe mercury problem, extensive mercury problem, but there are some water bodies, there are some places where concentrations are lower and you can lower your exposure. Also within each water body, there are species that have lower concentrations, another way to lower your exposure. So the story ends with a graphic from OEHA with the statewide advisory information for lakes and reservoirs. That's my story.
Thank you, Jay. And I'll kind of round this up and kind of backtrack to data visualization that I kind of helped, or at least I helped maintain it and update it now. But basically what you see on the screen here is the harmful algal bloom incident reports map, which is hosted on the HAB portal on the mywaterquality website. And basically the purpose of the map is just to show where these HABs are being reported statewide. And so all the data from the map comes from voluntary reports that are submitted via the HAB, and they're sending it to the state board. And we have a team in OLEMA, including Ali Dunn and Marissa Van Dyke, who are really processing those reports, getting checking the data, validating it, confirming it, following up, and feeding it into the database, which ultimately populates this map. So the map, each point on the map represents a reported location, and when you kind of scroll over one of these points, it shows more information related to that reported bloom. So it'll show you the date that the bloom was observed, it'll give you a description of the bloom, any relevant advisory information, and then also like the agencies involved with it. Really kind of when we sat down and discussed kind of how we would design this visualization, I think really kind of one of the main purposes of it was this map was to show kind of the current state of reported blooms statewide. So we wanted, managers and the public to be able to open this map and see, oh, here are all the current reported blooms, here are the hot spots, and we can decide from there how to respond to that. So the coloring of those points are really based on that kind of purpose we decided on. And the bright orange dots, those are kind of the most current ones. Basically, they've been reported within the last 7 days of today, the current date. And then the colors kind of fade to yellow, that kind of color, and then gray as it gets older and older. And so there are two parts to the visualization. There's the map, and then there's a table on the right, which doesn't really look that great right now, but the two parts are interactive. They are interconnected, so you can use the table to filter points on the map, or you can use, records. Okay, it's kind of slow right now, but it works. So, and then I guess I'll just I touched on this, but really we use Tableau Public for this visualization, which works great in terms of pushing these instant updates straight from my computer, for example. But it's there's a lot of work that goes into reviewing that data and checking it to make sure that we can display it on the map. But once it's in Tableau, there's not a whole lot of data manipulation that goes on. We're really just showing the locations of these reported incidents. So there's not a whole lot of programming, which Tableau is also great at. Tableau is a data visualization exploration tool, which you don't need to know programming to create something like this. So it's great for us because we often have to push these updates very quickly. But we update it daily. We manually pull from the database and update the map. But I just wanted to close this saying that this is very much a team effort. We've had multiple people on OEMA. They've had their hands on this at some point. Ali Dunn and Marissa Van Dyke, they are really the data managers, the program leaders who oversee what goes on this map. So it's very much a team effort, and we're constantly discussing how to make it better, more intuitive to use, and hopefully more useful as well. So that's my visualization, and closes the report. I wish we had more time to show you the whole report, but we encourage you to go to the SWAMP website and to pull it up from there and actually read the narrative and explore the visualizations for yourself. So that is on the SWAMP homepage, and you can access it from there. So thank you.
So I think we have an opportunity for questions of any of the panelists, if anyone has any. This is I'm extremely proud of the team, and I mean everyone on the team, and there's people that aren't on the stage that were part of the team, because it's not only the people-technology blend people blend that made it work, but the technology blend. So this is the Ezra platform that has Tableau embed visualizations. It has our Shiny embed visualizations. It has some Esri stuff, I think, in there too. And then it could eventually even take some of the JavaScript and other hard-coded or more interactive and even alternative technologies. So the technology is representing the team, which is really just amazing of a blend of talent. So thank you again. So any questions? So the question, I believe, I didn't hear it, I'm sorry, but it was, are you making your code publicly available so people can see the scripts? And I think that's Marcus, you, for the R question.
I would argue that's an everybody question.
Yeah.
I don't have. I did want to get on my soapbox for a second. I didn't do it earlier, but now's my chance. I drank the Kool-Aid a long time ago with open source programming and software, and I understand, that there's a range of products available for people to use, that caters to different needs and skill levels, and I'm all for that. Use whatever works for you. But my personal opinion is that it's so invaluable to keep everything within the same workflow and use version control. And so one way to do that is using R. There's definitely integrated ways to do that through GitHub, as you mentioned, as well as being able to share and reproduce what you're doing as a result. So that's, I would love to see more of that. I know that through a lot of these other platforms, there are ways to integrate. I've never kind of on the way because there is value in having the ability to make a script on your own that does precisely what you need and integrate that within the app itself rather than something you do external. Having a very streamlined workflow that integrates all of the working pieces is just invaluable for making these things scalable and having sort of provenance in the long term. So I would encourage folks to explore ways of doing that through sharing code, GitHub, as well as sort of thinking about ways to integrate some of these more specific methods to integrate the analysis with the actual data biz product.
So one of the reasons that we're doing such a more collaborative team is because we want to actually also reveal a waterborne data or a California water data center kind of a concept. It would be a virtual group of people that does this. And one of the parts of that standing up right now is a GitHub page that has some of the code like Python script that we use to publish our seeding data on mywaterquality.ca.gov, as well as some of other projects that are coming out of my shop. But it's not meant to be an OEMA project. This is like a partnership as usual. So what we'd love to do is explore how to do this, and I know GitHub just changed hands, so that's part of the conversation is what do we do now. But I appreciate that perspective so much, so thank you. Are there any other people that want to respond? Any other questions in the audience?
I was just going to ask if there's any opportunities for other folks to learn how to do some of these. Is there any training maybe that would be available that people can learn how to create their own data stories, or if you have the data stories but you don't know how to
Right.
these programs?
So I think, Michelle, you can definitely take the lead on most of this, but the platform itself, ArcGIS provides a story map platform with templates that is being used by lots of people, not just OEMA. And I think there's probably some either CAN training and or future training available through GIS Roundtable and people like that. When you get into the products like Shiny, Tableau, and what have you, we would love to be able to support that, and we can. We also, I forgot to mention Power BI. Microsoft actually has a decent product that could fit into here too. But what we'd like to do is to provide options, and many times the vendors of those products will do a certain amount of demo kind of training for free. And we've had Tableau already step up and help us a lot, and I think Microsoft is going to do the same. But for more intensive stuff, there's also lots of online courses, local courses, in-person courses. The Training Academy may be able to customize some stuff. We have a whole data literacy training initiative, so to speak, coming out of the open data resolution that we're planning to bring to the state board in 2 weeks, July 10th. We should be able to embrace principles of open data around the whole organization. And part of that is a data literacy component that includes how to provide the training to the organization. So, and I don't know if you have anything you want to add, Michelle, that you know.
Yeah, no, I think you're right. I think at least just with the State Water Board, I mean, man, yeah, there are so many resources out there, but I think it also depends what platform you might be interested in, because I think, like Greg said, there are a lot of choices. Some might be better than others depending on what you want to do. But I know at the State Water Board, as part of that initiative, we do have kind of like a data science club where a lot of people interested in data science, we can meet, talk about things that worked or didn't work for us, share resources that we found to be really helpful. So something like that, I think, at least for me, has been really valuable in terms of kind of choosing like what path I wanted to go through and like kind of deciding what's worthwhile and what's not.
How do you get into the club?
Yeah, you got to think of a sticker on the way out.
You need a tattoo.
From a workflow perspective, just as an observer, there's a ton, like the 90% rule maybe applies of preparing the data, structuring and shaping it, cleaning it up, getting it ready. And then what we'd like to do is to publish the high-value data sets to our open data portal, which is on the screen now. And if we can sort of build the workflow to get things like the SIPS data to flow up here, and the HAPS data I think currently flows up here. But all those high-value curated data sets ready to go, so to speak, here. The work of building a new map is a half an hour to 2 hours, depending on what you're trying to do, kind of a thing. So again, this is really, we're in this era now where if you do that hard work and invest in the sort of infrastructure to pipe the data to somewhere where it's accessible, you can do these kinds of things in a much easier way than it used to be.
My name is Claire, I'm from Mississippi Davis Utility. The question is regarding spatial data. I noticed a lot of people use ArcGIS for its analysis and also visualization. Just wondering if you have any open source GIS tools that you use, like QGIS, QDOL, and OCR. And if yes, how do you compare open source software versus enterprise software like ArcGIS? The support level of your product.
That's a good question. I haven't personally used the open source GIS software. I've actually only used ArcGIS software, just because that's what our agency has. But I know there has been a lot of requests to transfer or I guess translate our shape files to Google Earth KML files. So that's something that I think is open.
I'd like to comment on that. I think that's a really interesting and great question. Kind of like Marcus, I do really like the open source tools, and it would be my preference to use them in most cases. I think kind of at least the state board, the use, our access to ArcGIS, we have access to ArcGIS, we have an enterprise license, so it's very easy to bring up ArcGIS, and I think one of the big advantages it has over open source tools is that it's also easy to publish it. So we can publish it to ArcGIS Online. It's hosted on the ArcGIS Online servers, and we don't have to necessarily go through all of the kind of hoops that we would need to go through to kind of host those pages on our own. So in terms of just the publishing aspect, I think because we already have that infrastructure in place at our organization, that's usually what we choose to do. But I have used QGIS, I have used GDOL, and I think they're great analysis, great programs. I use them on my personal computer. But again, it kind of boils down to that, once you have that all there, how are we going to publish it and share it? And that's when it gets harder, because we need to find a host. And it's difficult to kind of at times to get that kind of IT support when our IT department supports ArcGIS already. So typically we choose ArcGIS for that.
Yeah, I'd like to follow up on that as well. The hosting issue is something that I think, venues like Esri are really helpful at, being able to push to the cloud. That sort of infrastructure is really helpful. But I also, on the other hand, want to make a plug for, again, using R for spatial analysis. I've definitely noticed a trend in the last couple of years of just more and more workshops at conferences or elsewhere that, how do you use R for spatial analysis? I would say 5 years ago, the tools weren't developed within R at a level to be able to do it sufficiently or easily. You definitely could, but now there's more, being that it's an open source programming language, there's some new packages that have come out recently. One in particular is the Simple Features package. If you look at that one, is a very easy way to work with spatial data in R that is an advance over some of the older packages. So if you're not afraid to use command line, it's really, really easy to use that package to do your standard geoprocessing work. So I would really strongly encourage folks to check that out if they want to think about ways to kind of streamline their analysis pipeline using open source software. But then again, when you talk about sort of scalability and stuff like that, it's not quite there, in terms of database hosting. That's a whole other different animal to think of. But in terms of doing the analysis and making your work streamlined, I think R is definitely at a place to do that very easily for many people.
So we're in the process of trying to get a Shiny server stood up, and so I understand what Michelle and others are talking about. It would be great, but we're making progress also to try to expand the tool. So if there aren't any other questions, I'll let everyone go home. And thank you very much for coming. And let's have a big round of applause for the Symposium team. And thank you all for participating.
Before you guys all leave, I wanted to say a couple thank yous. Thank you to the OLEMA staff for all the support the last couple of days and the weeks prior to this. Couldn't have done it without you. I wanted to thank SFEI, especially Jay Davis and Randy Turner for helping as well. Imagine H2O, they left, but they were very helpful, finding a great group of vendors. I want to thank all the presenters. I think the last 2 days, speakers and topics were fantastic, and I got a lot of good feedback. So I want to thank you all for your time. And just thank you for everyone for attending.